Hello there, and welcome to Science for Sleep, where curiosity drifts gently and the universe takes a quiet, meandering path to calm. Tonight, we're going to explore one of the most vast and unsettling phenomena that exists, not just in the corners of space we can see, but in the silent, uncharted expanses between galaxies. These are places so empty, so profoundly devoid of matter, that they challenge the very way we imagine space itself. Supervoids. Their name alone evokes a sense of emptiness, but it is in this emptiness, paradoxically, that the universe whispers some of its deepest secrets. We often think of space as a tapestry of stars, galaxies and planets, a canvas of brilliance stretching across the cosmos, but supervoids remind us that absence is just as significant as presence. They are the quiet gaps in the cosmic web, the places where galaxies are few and far between, and where even light seems to hesitate, travelling with nothing to illuminate. As you settle in, perhaps in a chair, a bed, or with the soft glow of a night lamp, I wonder, where are you watching from tonight? Is it late? The kind of late that makes you aware of every small sound in your room, or is it an early moment when the day is just beginning and the world outside is still stretching itself awake? Somewhere out there, across time zones, across continents, someone else is listening too, pondering the same emptiness, perhaps under the same stars, yet separated by distances that supervoids themselves would make seem trivial in comparison. The universe has this way of making us feel both connected and infinitesimally small at the same time, a duality that is especially apparent when we think about regions where even galaxies are scarce. If you find the quiet thought of supervoids intriguing, or simply a comforting way to drift into a slower pace after the noise of your day, it would mean a lot if you gave this video a like and maybe subscribed. This little corner of calm is dedicated to those who wish to explore the universe at a pace that doesn't rush, a pace that lingers and allows for wonder to settle gently over the mind. The act of learning about these enormous gaps, the immense nothingness, is not just an intellectual exercise. It's also an invitation to consider scale, perspective, and our own small yet remarkable existence in a universe that has room for both dazzling complexity and profound absence. Supervoids are not the kind of place you can visit, at least not in any practical sense. There are no spacecraft that have drifted into one to send back images of the emptiness, and yet astronomers have found them by carefully mapping the positions of millions of galaxies. These maps reveal the cosmic web, a vast network of filaments composed of stars, galaxies and dark matter, stretching across billions of light years. Within this web are enormous regions where the threads are missing, where galaxies are thinly scattered, and where the density of matter is remarkably low. The emptiness is relative, of course. Supervoids are not completely devoid of matter. They still contain dark matter, a few lonely galaxies here and there, and diffuse gas. But the scale of emptiness is staggering. Some supervoids span hundreds of millions of light years. To put that into perspective, the distance from our Sun to the nearest star, Proxima Centauri, is about 4.24 light years. A supervoid could fit tens of thousands of those distances across, a vast region almost incomprehensible to the human mind. Despite their intimidating size, supervoids do not threaten in the way we imagine danger. They are not black holes that pull objects toward a point of no return, nor are they filled with radiation or exotic forces that could harm a traveller. Instead, their impact is subtle, mostly affecting the movement of galaxies and the expansion of the universe itself. The sheer emptiness inside a supervoid means that gravitational forces are weaker there, allowing surrounding structures to accelerate slightly faster away from the void. In some ways, they are cosmic sculptors, shaping the distribution of matter on the larger scales without ever touching it directly. They are the negative space in the artwork of the cosmos, defining what is by showing what isn't. What makes supervoids so compelling is the way they force us to confront the idea of nothingness. Humans are not naturally equipped to think on scales of hundreds of millions of light years, or to imagine spaces almost entirely devoid of matter. Our brains are tuned for survival, for noticing patterns, for filling in gaps, not for appreciating emptiness at this scale. And yet, the existence of supervoids challenges our intuitions. They remind us that the universe is not just a collection of stars and planets, but a dynamic, evolving structure where absence has as much significance as presence. Looking at a map of the cosmic web with its filaments and voids, you see a universe that is both intricate and stark, a mixture of geometry and randomness that suggests both design and chance. The discovery of supervoids has not only changed how astronomers think about the large-scale structure of the universe, but has also influenced our understanding of cosmic history. Theories suggest that these voids formed over billions of years as gravity pulled matter into dense filaments and nodes, leaving behind enormous expanses where few galaxies coalesced. The growth of supervoids is slow and subtle, an almost imperceptible shift in the cosmic tapestry. Yet over time, these regions become increasingly empty relative to their surroundings. Observing them is challenging. Astronomers rely on large surveys, mapping millions of galaxies to identify areas where the density of matter drops significantly below the cosmic average. Even then, the boundaries are diffuse, not sharply defined, a reminder that emptiness is not always a neat concept. As you listen, it might be helpful to imagine the experience of floating through a supervoid. There are no bright stars nearby, no clusters of galaxies to anchor your gaze, no familiar points of reference, only darkness stretching across unimaginable distances. It's a place where the usual markers of scale and orientation dissolve, where the vastness presses gently against your awareness, not threatening, but humbling. For a human or any traveller accustomed to the presence of matter, the experience would likely be disorienting. Our minds are accustomed to perceiving space filled with objects, with points of reference. In a supervoid, even light travels mostly unimpeded, and the few galaxies that exist may be scattered far apart, like lonely islands in an infinite ocean. Yet, the quiet of supervoids is not total silence. There are faint whispers embedded in the cosmic microwave background. The residual radiation from the Big Bang ripples in space-time from distant gravitational events and subtle shifts in the motion of galaxies at the edges. Scientists detect these phenomena indirectly, interpreting data and looking for patterns that reveal the hidden presence of voids. One of the most famous examples is the so-called cold spot in the cosmic microwave background, a region cooler than its surroundings, which some theories link to a supervoid. Though the exact causes remain uncertain, the connection between such observations and the emptiness of supervoids illustrates how absence can influence what we perceive. There is also a philosophical element to considering supervoids. When we look at the night sky, we're used to marvelling at what is present, the bright stars, the glowing nebulae, the spiraling galaxies. Supervoids remind us that the universe is not only composed of what we can see, but also of vast regions where there is remarkably little. These spaces, these tremendous gaps, challenge our perception, inviting us to reflect on scale, on distance, and on the profound quiet that stretches across billions of light years. They are a counterpoint to the brilliance of galaxies, a reminder that emptiness is an integral part of the cosmos, just as much as matter and energy. Perhaps part of the fascination with supervoids comes from their extreme rarity. They are not common, though the universe is vast, and within this vastness, even rare phenomena become inevitable. When astronomers map the distribution of galaxies, they see a pattern that is both structured and sporadic, filaments connecting nodes, with supervoids interrupting the web in unexpected ways. Some supervoids are enormous, stretching hundreds of millions of light years, while others are smaller, less dramatic, but no less significant for our understanding of cosmic evolution. Each supervoid tells a story, not of what exists, but of what was drawn away, of matter gathered elsewhere, leaving behind the silent spaces that shape the universe. Even as we consider these gaps, we might reflect on what they mean for us as observers. Supervoids do not influence our daily lives directly. We do not feel their emptiness, nor do they impose upon us any tangible danger. Yet they expand our sense of possibility, showing that the universe is not only a place of light and substance, but also of vast, unfathomable absence. There is something quietly humbling about imagining a region where the nearest galaxy might be millions of light years away, where space itself seems to stretch endlessly without the usual landmarks. In this sense, supervoids are both unsettling and beautiful. They are reminders of scale, of the limits of perception, and of the richness of emptiness. So as you settle deeper into your space of calm, perhaps closing your eyes or letting your attention drift gently, imagine the quiet stretches of the universe, the supervoids that span hundreds of millions of light years, untouched and untroubled. Imagine the rare galaxies scattered across this darkness, drifting slowly under the influence of gravity, the subtle pull of surrounding filaments shaping their path. It is a universe that is patient, indifferent to our schedules, our concerns, our small rhythms of daily life, yet it is also a universe that invites wonder, curiosity, and gentle reflection. And as we begin this journey into these astonishing regions, know that the emptiness we explore is not a void in knowledge or imagination, but an invitation to expand both. As we begin to peer more closely into the cosmos, it becomes clear that supervoids are not simply empty pockets floating aimlessly in space. They are vast, quiet giants, stretching across hundreds of millions of light years, the silent architects of the universe's large-scale structure. Their enormity is difficult to comprehend, and imagining their scale requires us to step far beyond the familiar distances of our solar system. When we look at the night sky from Earth, the stars appear close, the moon and planets comfortably within reach of our imagination, and even nearby galaxies like Andromeda feel tangible when seen through telescopes. But a supervoid dwarfs all of these familiar cosmic objects by orders of magnitude. To give you a sense of scale, if the Milky Way were reduced to the size of a grain of sand, a supervoid might stretch across an entire football field, or even several fields laid end to end. The distances involved are so vast that they escape the intuitive understanding our brains are wired for, yet they are very real, measurable, and profoundly influential in shaping the cosmos. These regions are defined by the relative absence of galaxies and matter. In the denser regions of the cosmic web, galaxies cluster together in groups, clusters, and filaments, connected by invisible threads of dark matter. Supervoids, in contrast, are sparsely populated, with galaxies scattered so thinly that the spaces between them are almost entirely empty. Some voids contain fewer than 1/10 the number of galaxies found in an average volume of space. The lack of matter is not merely aesthetic, it has consequences for the behavior of surrounding structures. Gravity is weaker inside a void, meaning that the few galaxies that do exist experience less gravitational tug from nearby matter. Over billions of years, this creates a gentle, almost imperceptible expansion of emptiness, as surrounding matter is gradually drawn into denser regions while the void itself grows ever larger. Interestingly, the emptiness of supervoids is not uniform. Some contain small filaments or clusters of galaxies, though these are exceptions rather than the rule. These sparse galaxies are often dwarfed by their counterparts in denser regions, struggling to form stars at the rate seen elsewhere. Observations suggest that galaxies inside or near voids may evolve differently, sometimes appearing smaller, fainter, and less structured than those in crowded cosmic neighborhoods. In this way, supervoids act as laboratories for studying the influence of environment on galaxy formation and evolution. They allow astronomers to see how galaxies behave when stripped of many of the forces and interactions that shape the universe in its more populated regions. The quietness of supervoids is also physical in nature. Light travelling through these regions is less likely to encounter matter, meaning that, in principle, there is less scattering, fewer gravitational perturbations, and a subtle difference in the temperature of the cosmic microwave background across their span. This has led to the discovery of phenomena such as the cold spot, a patch of sky cooler than surrounding regions, which may be linked to a supervoid lying hundreds of millions of light years away. The cold spot is an example of how supervoids, despite their emptiness, can leave detectable imprints on the universe, influencing the radiation and energy that passes through them. Observing these effects requires careful mapping, precise measurements, and a willingness to explore spaces that, at first glance, might seem unremarkable simply because they contain so little. The origins of supervoids are tied to the earliest moments of the universe. When the universe was young, shortly after the Big Bang, matter was not evenly distributed. Small fluctuations in density existed, tiny variations that would grow over time under the influence of gravity. Denser regions attracted more matter, forming the seeds of galaxies and clusters, while underdense regions lost matter to these gravitational wells. Over billions of years, these underdense regions expanded, becoming the supervoids we detect today. Their existence is a natural outcome of cosmic evolution, a reminder that emptiness is not mere absence, but an active participant in shaping the universe. The largest supervoids, stretching across nearly 1 billion light-years, are rare but powerful evidence of how initial conditions and gravitational dynamics collaborate on scales beyond ordinary human comprehension. Observing these voids presents unique challenges. Unlike galaxies or clusters that emit light, supervoids are defined by what isn't there, a subtle difference in density that requires immense data sets and careful statistical analysis to identify. Astronomers use surveys mapping millions of galaxies to trace the cosmic web, noting where galaxies thin out and voids emerge. These surveys, such as the Sloan Digital Sky Survey, have revealed the network of voids, filaments, and clusters that compose the large-scale structure of the universe. By mapping where galaxies are missing, scientists can chart the location, size, and shape of supervoids, and even begin to understand their influence on surrounding matter and radiation. The influence of supervoids extends beyond the absence of galaxies. Gravity, that ever-present sculptor, behaves differently in and around voids. The low density within a supervoid allows the surrounding matter to move with slightly less resistance, subtly affecting the expansion rate of nearby regions. This can lead to what cosmologists call the integrated Sachs-Wolf effect, a phenomenon where light travelling through a supervoid experiences a tiny shift in energy. Detecting such subtle shifts provides evidence for the void's existence and helps astronomers understand the interplay between matter, energy, and space-time on the larger scales. These effects are almost imperceptible in everyday terms, yet they are measurable across cosmic distances and provide crucial clues about the universe's expansion and composition. While supervoids are defined by emptiness, they are far from simple. Their shapes are irregular, often elongated or lumpy rather than perfectly spherical. They can contain smaller voids within themselves, nested layers of emptiness, or thin filaments bridging parts of the void. This complexity reflects the chaotic, dynamic nature of the universe, where initial density fluctuations evolve under gravity, dark energy, and cosmic expansion into structures that are simultaneously simple in concept, yet astonishing in detail. Studying these patterns helps cosmologists refine models of structure formation, revealing how the delicate balance of forces over billions of years creates the large-scale tapestry we observe today. The quiet giants are also reminders of perspective. While we often think about objects in the universe as discrete and countable, such as stars or galaxies, supervoids exist to challenge that assumption. They are vast, almost invisible in the night sky, yet their impact is measurable, their presence undeniable. They stretch our imagination and confront us with the scale of emptiness, asking us to consider what it means for something to exist in relative absence, how gravity and expansion operate without the interference of dense structures, and how our own observations are influenced by the spaces in between. Imagine for a moment drifting across a supervoid, There are no nearby galaxies to catch the eye, no dense clusters to mark position. Light moves uninterrupted, and the surrounding space is shaped not by the presence of matter, but by the vastness of its absence. Even the faint glow of the cosmic microwave background offers little guidance, slightly altered but largely uniform, a soft hum of the universe's history stretching across billions of years. The sensation is both humbling and strangely comforting, a reminder of scale, of patience, and of the universe's capacity for both presence and absence. It is in this emptiness that the universe shows one of its most understated qualities: quiet persistence. Even without the brilliance of stars or the density of galaxies, the structure of space continues, evolving slowly, quietly, relentlessly. Studying supervoids also raises subtle questions about the nature of space itself. When we measure distances, map velocities, and track the expansion of the universe, the low-density regions behave slightly differently than denser areas. The expansion of space in voids can be fractionally faster, a gentle stretching that affects light travelling through them. In this sense, supervoids are not entirely passive. They participate in the dynamic evolution of the cosmos, guiding the motion of matter around them, and subtly influencing the large-scale flow of galaxies. In addition, their sheer scale provides a window into cosmology, helping us test theories of dark energy, the mysterious force accelerating cosmic expansion, and the underlying geometry of space-time. Even though supervoids are extreme and unsettling, they are not dangerous in the conventional sense. They do not suck matter into a singularity, nor do they emit harmful radiation or pose a threat to observers. Their significance lies in scale, absence, and subtle influence. They are reminders of the universe's diversity, showing that emptiness can be just as informative as presence. By studying these vast regions, astronomers gain insights into galaxy formation, cosmic expansion, and the distribution of dark matter. Every supervoid mapped is another step in understanding how the universe grew from a nearly uniform state after the Big Bang to the richly structured cosmos we inhabit today. Perhaps the most astonishing aspect is that these giants, these tremendous spaces, are both empty and essential. Without them, the cosmic web would be denser, the universe less structured, galaxies more crowded, and the evolution of matter less predictable. The gaps, the emptiness, provides the context in which structures form, a negative space that shapes the universe as much as the filaments themselves. Supervoids are proof that absence is not nothing, but a subtle, powerful presence on scales that challenge human intuition. And as you let these thoughts drift, consider your place in this vast web of structure and emptiness. While our daily lives unfold in rooms, cities, and planets, the universe stretches on incomprehensibly, containing giants of quiet, empty space that dwarf our imagination. In them we find scale, patience, and the astonishing fact that the universe is as much about what isn't there as what is. It becomes necessary to pause and truly consider the scale of these supervoids. The emptiness we are discussing is not like the quiet spaces of a room at night, not like the stillness in a forest before dawn. This is a vast cosmic emptiness, stretching across hundreds of millions of light years, distances so immense that even light, which is the fastest traveller in the universe, takes millions of years to cross them. To truly grasp the magnitude of a supervoid, it helps to step outside the confines of our familiar thinking, to imagine a space so vast that even galaxies appear as distant specks, and the distances between them feel more like gulfs than neighbourhoods. When we consider the largest supervoids discovered, we enter a realm of nearly incomprehensible scale. One of the most famous, often referred to simply as the Eridanus supervoid, stretches approximately 1 billion light-years across. To put this into perspective, the Milky Way is about 100,000 light-years across. This means that this supervoid could fit roughly 10,000 Milky Ways side by side, and there would still be room left over. Our human minds, accustomed to thinking in kilometres or even astronomical units within our solar system, struggle with numbers of this magnitude. Yet, these measurements are real, observable, and scientifically verified. They are based on the positions of millions of galaxies mapped across the sky, statistical analyses of cosmic structures, and the subtle effects that such emptiness has on the light that travels through it. It is tempting to think of supervoids as simple, spherical bubbles of nothing, but the reality is far more irregular. Their shapes can be elongated, lumpy and uneven, with faint filaments of matter running through them, like faint scratches across an otherwise smooth surface. The edges of a supervoid are not sharply defined. There is no sudden drop from dense galaxy clusters into empty space. Instead, there is a gradual thinning, a diffuse transition where galaxies become increasingly scarce. Observing and defining the boundaries of these voids is therefore a careful and delicate process. Astronomers map the density of galaxies, identifying areas where the concentration falls significantly below the cosmic average. Even within these voids, a few galaxies may remain, scattered like distant buoys in a silent ocean. To imagine moving through such a void is both humbling and disorienting. A spacecraft traversing the supervoid would encounter very few galaxies along the way. Light from surrounding structures would appear faint, stretched thin across enormous distances. The usual cosmic landmarks, the dense clusters and bright nebulae we associate with the night sky, would be absent, leaving a pervasive, almost monotone emptiness. Even the cosmic microwave background, the faint glow left over from the Big Bang, would offer little variation, a subtle uniformity that reinforces the sense of isolation. Time and distance in such a place take on a different quality, not in a literal sense, but in the perception of vastness. The mind struggles to reconcile the smallness of individual galaxies with the immensity of the space separating them. The emptiness of supervoids is more than a curiosity, it has measurable consequences. One of the subtle effects astronomers have detected is known as the integrated Sachs-Wolf effect. As light from distant galaxies travels through a supervoid, the gravitational pull within the void is weaker, causing the light to experience a tiny shift in energy. This results in a minute cooling effect when observing the cosmic microwave background, which has been linked to the mysterious cold spot in the sky. It is remarkable to consider that these regions, defined largely by absence, can leave detectable imprints on the universe's radiation, proving that emptiness itself has influence. Supervoids also challenge our perception of speed and movement on a cosmic scale. In denser regions, the gravitational pull of nearby galaxies affects the motion of stars and galactic clusters. Inside a supervoid, the scarcity of matter means that galaxies experience less gravitational drag, allowing them to drift slightly faster along the expansion of the universe. Over billions of years, this subtle effect contributes to the growth of the void, expanding its boundaries as matter is drawn toward denser filaments surrounding it. The void is both passive and active in shaping the cosmos. Its emptiness may appear inert, but its presence influences the dynamics of the universe, guiding the distribution of galaxies and the flow of energy across unimaginable distances. One of the most astonishing aspects of supervoids is their age. These regions began forming shortly after the universe itself took shape. In the moments following the Big Bang, matter was not evenly distributed. Small fluctuations in density existed, tiny variations that would grow over time under the influence of gravity. Denser regions accumulated matter, forming the seeds of galaxies and clusters, while under-dense regions gradually emptied, becoming the voids we observe today. Supervoids are therefore ancient, a direct imprint of the universe's earliest moments, preserved on a scale so large that it stretches across billions of light-years. They are cosmic fossils, relics of a time when the universe was still organizing itself into the structures we see now. The perception of emptiness on these scales can be disquieting. Humans are wired to interpret empty spaces in terms of danger or absence, to feel unease in vast unknowns. In the context of a supervoid, that instinct is amplified. Imagine looking up at a map of the universe where 1 billion light-years of space contain only a few scattered galaxies. The mind searches for landmarks, for reference points, and finds almost nothing. The sensation is akin to standing on a beach stretching endlessly in all directions, without the ocean, without the horizon, just sand that continues without limit. It is not fear in the physical sense, but a profound awareness of scale, isolation, and the limits of comprehension. Yet, the emptiness also has its own kind of beauty. Supervoids reveal the universe in its most subtle form, showing that structure is defined not only by presence, but also by absence. Without these vast gaps, the cosmic web would be denser, more uniform, and perhaps less dynamic. The interplay between filaments, clusters, and voids is essential for the evolution of galaxies, the formation of stars, and the overall growth of the universe. In a sense, supervoids are the negative space that allows the universe to take shape, reminding us that absence can be as vital as substance. There is also a philosophical element to contemplating these regions. The emptiness challenges assumptions about existence, about scale, and about our perception of the universe. It invites reflection on the vastness of space and our place within it. While we are accustomed to filling our surroundings with objects, experiences, and reference points, the supervoid offers almost nothing to hold on to. In this emptiness, perspective shifts. Human concerns shrink. Daily schedules and obligations become momentary, and the mind is offered a rare opportunity to consider scale, patience, and the gentle persistence of the universe over billions of years. Supervoids are not static. Their boundaries shift gradually over time, influenced by the slow movement of matter and the expansion of the universe itself. The galaxies at the edges of voids respond to gravitational gradients, slowly migrating toward denser filaments while leaving the void interior increasingly empty. Observations indicate that supervoids grow larger over billions of years, a process so slow that it is imperceptible on human timescales, yet dramatic on the scale of the cosmos. The quiet, relentless expansion is a reminder that even emptiness participates in the universe's evolution, not through action, but through the absence of interference. It is worth considering how supervoids relate to other extreme phenomena in the cosmos. Black holes, for instance, concentrate matter to an extreme degree, creating regions of intense gravity and space-time curvature. Supervoids, by contrast, represent the opposite extreme, regions of almost nothingness, where gravity is weaker and matter is scarce. Yet both are remarkable, both are extreme, and both reveal the extraordinary range of conditions that the universe can produce. One is a locus of concentrated power, the other a vast expanse of near inertia, and together they show the universe's capacity for diversity on the grandest scales imaginable. As we let these ideas settle, it is fascinating to consider how supervoids are mapped. Astronomers rely on large-scale surveys, cataloguing the positions of millions of galaxies across the sky. By identifying regions where galaxies are sparse, researchers construct three-dimensional maps of the universe's structure, revealing the cosmic web and the voids within it. The precision required is immense, relying on careful measurements, statistical analysis, and the ability to detect subtle patterns in otherwise sparse data. Each supervoid identified is a triumph of observation, computation, and interpretation, turning vast emptiness into something measurable and comprehensible. Even though these voids are largely devoid of galaxies, they are not entirely empty. There is dark matter, the mysterious substance that exerts gravitational influence without emitting light, as well as diffuse gas and occasional isolated galaxies. This residual content is often enough to subtly influence the paths of light and the motion of nearby structures, meaning that supervoids are never truly inactive. Their emptiness is relative, but even in its subtlety, it has profound effects on the universe's evolution. In this sense, supervoids are both nothing and something, a paradox that challenges our intuition while offering insights into the workings of the cosmos. reflecting on supervoids encourages a unique form of meditation. Unlike clusters of galaxies, nebulae or stars, which attract attention through brilliance or complexity, supervoids captivate through subtlety, scale, and absence. Imagining these enormous spaces with galaxies scattered across hundreds of millions of light years can evoke a quiet contemplation of the universe's immensity. It is a place where time, space, and scale become abstract, where the mind is invited to relax into the incomprehensible vastness and to recognize both the insignificance and the uniqueness of our own place in the cosmos. Not far from the dense clusters of galaxies and the bright knots of cosmic structure, there exist regions where the universe becomes astonishingly sparse, places where distance takes on an entirely different meaning. These are the loneliest regions in space, the interiors of supervoids, where galaxies are not just rare, but separated by expanses so vast that even imagining the nearest neighbour becomes an exercise in stretching the limits of thought. What defines loneliness here is not emotion, of course, but separation, an immense physical distance between islands of matter, where the usual cosmic crowd simply fades away. In most parts of the universe, galaxies tend to gather. Gravity encourages them to cluster, to form groups and superclusters, to connect through filaments of dark matter that weave the cosmic web together. Our own Milky Way belongs to a modest collection called the Local Group, surrounded by neighbouring galaxies like Andromeda and the Triangulum Galaxy. Even beyond that, there are larger structures, clusters containing hundreds or thousands of galaxies, all bound together in a kind of cosmic community. Movement, interaction, and gravitational influence are common in these regions. Galaxies pass near one another, merge over time, and exchange streams of stars and gas. Inside a supervoid, that familiar sense of cosmic neighbourhood dissolves. Instead of nearby companions, a galaxy might find itself separated from the next by tens of millions of light years, sometimes even more. If you were positioned within such a galaxy and looked out into the surrounding space, the sky would appear far emptier than what we see from Earth. There would be fewer bright smudges of distant galaxies, fewer clusters glowing faintly in the darkness. The universe would feel stretched thin, as though its contents had been gently pulled apart, leaving only a sparse scattering behind. The concept of distance changes in a place like this. On Earth, even a remote desert or an open ocean still offers points of reference, horizons, landmarks, subtle variations that help the mind orient itself. In a supervoid, those references are almost entirely absent. Space does not offer edges or boundaries in the way we expect. It simply continues, uniform and vast, with only occasional interruptions where a lonely galaxy drifts along its slow path through cosmic time. The nearest large structure might be so far away that its light takes hundreds of millions of years to arrive, meaning what you see is not just distant in space, but distant in time as well. This isolation has consequences for the galaxies that inhabit these regions. Without frequent interactions, mergers become rare. Galaxies evolve more quietly, without the dramatic collisions that can trigger bursts of star formation or reshape their structure. Observations suggest that void galaxies are often smaller, less active, and more isolated in their development. They form stars at a slower pace, sometimes maintaining simpler shapes for longer periods compared to their counterparts in crowded environments. In this sense, the loneliness of a supervoid influences not only where galaxies are, but how they grow and change over billions of years. Gravitational influence, which dominates so much of cosmic behaviour, becomes noticeably weaker in these regions. In dense clusters, gravity pulls strongly, guiding the motion of galaxies and binding them together. Within a supervoid, the pull is softer, less directional. Galaxies are not drawn into tight orbits or dramatic interactions. Instead, they drift more gently, their motion shaped by the broader expansion of the universe rather than by close gravitational encounters. Over immense stretches of time, this leads to a subtle but persistent effect. Matter continues to migrate outward from the void's centre toward its edges, leaving the interior even emptier. This gradual evacuation is not sudden or violent. It is a slow, almost imperceptible process, unfolding over billions of years. Galaxies near the centre of a void feel slightly stronger gravitational attraction toward denser regions outside, and over time, they move in that direction. The result is that supervoids tend to grow larger, their interiors becoming increasingly sparse as matter drifts away. The loneliness deepens, not because something dramatic happens, but because nothing interrupts the quiet redistribution of matter. Light too behaves differently in these vast empty regions. When photons travel through denser areas of the universe, they encounter gravitational fields that can bend their paths, a phenomenon known as gravitational lensing. In a supervoid, with far less matter to influence them, light travels in a straighter, less disturbed path. However, the absence of gravitational wells also means that light does not gain energy in the same way it might when falling into a dense region. Instead, it can lose a small amount of energy as it crosses the void, contributing to subtle temperature variations in the cosmic microwave background. Even the background radiation of the universe, that faint afterglow from the Big Bang, reflects the presence of these lonely regions. When astronomers map this radiation, they sometimes detect cooler spots that correspond to supervoids. These areas appear slightly different not because something is actively happening there, but because less is happening. The lack of matter leaves a measurable imprint, a quiet signature that reveals the existence of vast emptiness without directly observing it. Imagining a journey through such a region brings a unique perspective. Suppose a spacecraft could travel for millions of years across a supervoid. The crew, if such a journey were possible, would encounter long stretches of darkness punctuated only occasionally by distant galaxies. There would be no dramatic encounters, no sudden changes in scenery. Instead, the experience would be one of continuity, a steady, unchanging backdrop that emphasizes the sheer scale of the emptiness. The sense of movement might even feel diminished, as there would be few visual cues to indicate progress. Orientation in such a place would rely heavily on distant reference points. Without nearby stars or galaxies to guide direction, navigation would depend on precise measurements of position relative to faraway structures. The concept of near and far would shift dramatically. What we consider distant in everyday terms would feel immediate compared to the distances separating galaxies within the void. It is a reminder that scale in the universe is not fixed, but relative, expanding or contracting depending on where you find yourself. There is also an interesting psychological dimension to considering these regions. Humans tend to associate emptiness with absence, with a lack of activity or meaning. Yet in the context of the universe, these vast empty spaces are integral to its structure. They define the boundaries of clusters and filaments, shaping the distribution of matter in ways that would not occur if space were uniformly filled. The loneliness of a supervoid is not a flaw or an anomaly, but a natural outcome of cosmic evolution, a necessary counterpart to the dense regions that capture our attention. Looking at the larger picture, the universe resembles a kind of foam or sponge, with dense regions forming the walls and supervoids creating the bubbles in between. This structure arises from the initial conditions set shortly after the Big Bang, amplified over billions of years by gravity and cosmic expansion. The result is a universe that is neither uniform nor random, but patterned in a way that balances density and emptiness. The loneliest regions are just as important as the most crowded ones, each playing a role in the overall architecture. One might wonder whether anything could exist comfortably in such isolation. From a physical standpoint, there is nothing inherently hostile about a supervoid. It is not filled with harmful radiation, nor does it exert destructive forces. The challenge lies in the sheer distances involved. Any form of communication, travel, or interaction would be limited by the immense separation between objects. Signals would take millions or billions of years to cross the void, making real-time interaction impossible. In that sense, the loneliness is not dangerous, but it is absolute. Despite this, the few galaxies that do inhabit these regions continue their quiet existence. Stars form, planets orbit, and the processes of astrophysics unfold just as they do elsewhere, albeit at a different pace and with fewer external influences. From within one of these galaxies, the inhabitants, if any existed, might not even be aware of their isolation without careful observation. Their local environment would feel normal, even if the broader cosmic context is one of extreme separation. Considering this perspective brings an interesting realization. Loneliness, on a cosmic scale, is relative. A galaxy within a supervoid might seem isolated when viewed from the outside, but from within, it still contains billions of stars, potentially countless planetary systems, and all the complexity that comes with them. The emptiness lies between galaxies, not within them. This distinction highlights how scale influences perception, how what appears empty on one level can still contain richness and structure on another. Over time, as observations improve and surveys become more detailed, astronomers continue to refine their understanding of these regions. New supervoids are identified, their shapes and sizes mapped with increasing precision. Each discovery adds another piece to the puzzle, helping to reveal how matter is distributed across the universe and how the interplay of gravity and expansion has shaped its evolution. The loneliest regions, once overlooked because they contain so little, have become key to understanding the whole. As this exploration continues, the quiet nature of supervoids remains one of their defining features. They do not announce themselves with bursts of light or dramatic events. Instead, they exist as subtle patterns in the distribution of galaxies, detectable only through careful observation and analysis. Their presence is felt through absence, their influence measured through the behavior of light and matter passing through them. Allowing the mind to settle on this idea, the vastness of these regions becomes less unsettling and more contemplative. The universe is not only a place of dazzling complexity, but also one of profound simplicity, where emptiness stretches across unimaginable distances without interruption. In these spaces there is no rush, no urgency, only the slow, steady unfolding of cosmic time. If you could step far enough away from everything, beyond galaxies, beyond clusters, beyond even the largest structures we usually talk about, the universe would begin to reveal a pattern. Not a random scattering of matter, not a chaotic spread of stars, but something surprisingly organized. Something delicate, almost lace-like in its structure. This vast arrangement is what astronomers call the cosmic web, and it is within this immense network that supervoids, those quiet giants we've been drifting through, find their place. The name itself gives a hint of what to expect. A web suggests threads, connections, intersections, and spaces in between. And that is exactly what the universe looks like on its largest scales. Galaxies are not spread evenly throughout space. Instead, they gather along enormous filaments, long thread-like structures composed of galaxies, gas, and dark matter. These filaments stretch across hundreds of millions of light years, linking together dense nodes where galaxy clusters reside. Between these threads lie the supervoids, vast regions where matter is scarce, completing the pattern like the open spaces in a net. This structure did not appear by chance. Its origins trace back to the earliest moments of the universe, when tiny fluctuations in density were imprinted shortly after the Big Bang. These fluctuations were incredibly small, differences of just a fraction of a percent, but they were enough. Over time, gravity began to amplify these variations. Regions that were slightly denser pulled in more matter, growing into filaments and clusters. Meanwhile, regions that were slightly less dense lost matter to their surroundings, becoming the voids we now observe. The cosmic web is the result of billions of years of this process, a slow and steady shaping of matter under the influence of gravity. Looking at simulations of the universe's evolution, you can see this process unfold. Initially, matter is almost evenly distributed, a faint, grainy texture across space. Then, as time passes, that texture begins to stretch and pull. Filaments emerge, connecting dense nodes like strands of a vast network. The voids expand, becoming larger and emptier. By the present day, the universe has transformed into this intricate web, a balance of structure and emptiness that spans the observable cosmos. The scale of the cosmic web is difficult to overstate. Individual filaments can be hundreds of millions of light-years long, and clusters at their intersections can contain thousands of galaxies. The entire web stretches across the observable universe, a structure so large that it defines the very framework within which galaxies exist. Supervoids, in turn, are not isolated anomalies, but essential components of this framework. They are the spaces between the threads, shaping the overall geometry of the universe. One of the most fascinating aspects of the cosmic web is the role of dark matter. Although we cannot see it directly, dark matter makes up the majority of the universe's mass, and it plays a crucial role in forming the web's structure. The filaments are believed to be composed largely of dark matter, with galaxies forming along these invisible scaffolds. In a sense, the luminous matter we observe, stars, galaxies, gas, is just the visible tracing of a much larger hidden network. The web exists whether we can see it or not, with dark matter providing the gravitational backbone that holds it together. Supervoids, then, are regions where this dark matter is also sparse. They are not completely devoid of it, but the density is significantly lower than in the filaments and clusters. This difference in density is what creates the contrast between the threads and the gaps. The web is not made of solid lines and empty holes, but of gradients, where matter gradually becomes more or less concentrated. Still, the contrast is strong enough that the pattern is unmistakable when mapped on large scales. Mapping the cosmic web is one of the great achievements of modern astronomy. Large surveys, such as those conducted over decades, have catalogued the positions of millions of galaxies, allowing scientists to reconstruct the three-dimensional structure of the universe. When these data are plotted, the web emerges clearly. Dense clusters appear as bright nodes, filaments stretch between them, and supervoids open up as vast, dark regions. It is a picture that is both complex and elegant, revealing order on a scale that was once unimaginable. The connections within the web are not just visual, they are dynamic. Matter flows along the filaments, drawn by gravity toward the dense nodes. Galaxies can move along these structures, sometimes merging with others as they travel. Gas flows through the filaments as well, feeding star formation in galaxies and contributing to their growth. The web is not static but alive with motion, a slow and continuous redistribution of matter across the universe. Within this context, supervoids take on a new significance. They are not merely empty spaces but the counterbalance to the filaments. As matter flows into the threads, it leaves behind these vast regions of low density. The expansion of the universe further accentuates this process, stretching the voids and making them larger over time. The cosmic web, therefore, is shaped by both attraction and expansion, by the pull of gravity and the push of cosmic growth. Imagining the cosmic web from within a galaxy is challenging because we are embedded in it. From our perspective, the universe appears as a sky filled with stars and distant galaxies, without an obvious pattern. It is only when we step back using maps and simulations that the web becomes visible. This shift in perspective is essential. It reminds us that our local view is limited, and that the true structure of the universe reveals itself only when we consider it on the larger scales. There is something quietly remarkable about this structure. Despite the immense complexity of the universe, with its countless galaxies and stars, the large-scale pattern is relatively simple. Threads and gaps, filaments and voids, repeating across vast distances. It is a kind of cosmic symmetry, not perfectly regular, but consistent enough to be recognizable. This simplicity emerging from complexity is a recurring theme in nature, and the cosmic web is perhaps one of its most striking examples. The presence of supervoids within this web also influences how we observe the universe. Light travelling from distant galaxies must pass through both dense regions and voids, and this journey affects what we see. Gravitational lensing, redshift, and other effects can alter the appearance and properties of distant objects. Understanding the structure of the cosmic web helps astronomers interpret these observations more accurately, providing context for the data we collect. Even the expansion of the universe is tied to this structure. Dark energy, the mysterious force driving the accelerated expansion of space, interacts with the distribution of matter in subtle ways. In regions of low density, such as supervoids, the effects of expansion can be more pronounced. This means that the cosmic web is not just a static arrangement, but a dynamic system influenced by forces that operate on the larger scales. Reflecting on this, the relationship between the web and the voids becomes clearer. They are not separate entities, but two aspects of the same structure. The filaments define where matter is concentrated, while the voids define where it is not. Together, they create the pattern that shapes the universe. Without the voids, the filaments would not stand out. Without the filaments, the voids would not exist. It is a balance, a continuous interplay between presence and absence. From a more contemplative perspective, the cosmic web offers a way to think about connection and separation on a universal scale. Galaxies are linked through these vast structures, yet separated by enormous distances. Supervoids emphasize that separation, stretching the spaces between connections to their limits. And yet, everything remains part of the same system, woven together by gravity and the fabric of space-time. Considering all of this, the universe begins to feel less like a random collection of objects, and more like a cohesive whole. The web provides structure, the voids provide contrast, and together they form a pattern that has evolved over billions of years. It is a reminder that even on the larger scales there is a kind of order, a framework that underlies the apparent chaos. As the mind settles into this image, threads of galaxies stretching across unimaginable distances, with vast empty regions in between, it becomes easier to see how everything fits together. The loneliness of supervoids is not isolation in a disconnected sense, but part of a larger design. They are the spaces that allow the web to exist, the gaps that give shape to the threads. And with that picture in place, it becomes natural to wonder how such an intricate structure first began to take form, how the early universe, once nearly uniform, transformed into this vast network of filaments and voids that continues to evolve even now. Long before galaxies had names, before stars began to shine in recognizable patterns, and even before the cosmic web stretched itself into the intricate structure we've just explored, the universe existed in a state that was almost perfectly uniform. Not completely smooth, but close enough that the differences were incredibly subtle. If you could have observed it then, you wouldn't have seen clusters or filaments or vast empty regions. Instead, there would have been a nearly even distribution of matter and energy, a quiet beginning where everything was present, but nothing yet stood out. Within that early simplicity, however, there were tiny imperfections. These were not dramatic gaps or dense clumps, but minute fluctuations, slight variations in density scattered across space. Some regions contained just a little more matter than average, while others had just a little less. The differences were incredibly small, measured in fractions of a percent, yet they carried enormous significance. These slight imbalances would become the seeds from which all large-scale structure in the universe eventually grew, including the supervoids we are now considering. Gravity, the patient and persistent force that shapes so much of the cosmos, began to act on these fluctuations. In regions where matter was slightly denser, gravity pulled more material inward, gradually increasing the density further. This created a feedback effect. The more matter gathered, the stronger the gravitational pull became, attracting even more matter over time. These regions would eventually grow into the filaments and clusters of galaxies that define the cosmic web. At the same time, the opposite process was unfolding in the less dense regions. Areas that started with slightly less matter experienced a different kind of evolution. Instead of drawing material inward, they effectively lost matter to their denser neighbours. Gravity from surrounding regions pulled matter away, leaving these areas increasingly underdense. Over vast stretches of time, these subtle differences amplified, transforming what were once barely noticeable variations into the enormous supervoids that span hundreds of millions of light-years today. This process did not happen quickly. It unfolded over billions of years, guided by the steady expansion of the universe. As space itself stretched, the distances between regions grew, but the underlying pattern remained. Dense areas continued to attract matter, becoming more pronounced, while underdense areas expanded and emptied out. The growth of voids is therefore closely tied to the overall expansion of the universe, a quiet partnership between gravity and cosmic stretching that shapes the distribution of matter on the larger scales. It is helpful to imagine this process as a kind of cosmic sorting. Matter flows toward regions of higher density, leaving behind pockets of emptiness that grow larger over time. These pockets do not remain static. As they expand, they push against the surrounding filaments, subtly influencing the shape and arrangement of the cosmic web. The boundaries of a void are not rigid walls, but shifting regions where the density gradually increases. This makes the edges of supervoids diffuse and complex rather than sharply defined. One of the remarkable aspects of this evolution is how predictable it is, given the initial conditions. Modern cosmological simulations using powerful computers and detailed physical models can recreate the formation of the cosmic web from these early fluctuations. Starting with a nearly uniform distribution of matter, the simulations show filaments forming, clusters growing, and voids expanding, all emerging naturally from the interplay of gravity and expansion. When compared to actual observations, these simulations match remarkably well, providing strong evidence that our understanding of the universe's large-scale evolution is on the right track. Despite this, there is still much to learn about the birth and growth of voids. The exact role of dark matter, for instance, is crucial but not fully understood. Dark matter does not emit light, but it exerts gravitational influence, and it appears to form the scaffolding upon which visible matter gathers. In the early universe, dark matter likely played a dominant role in shaping the initial density fluctuations, guiding the formation of both dense structures and voids. Understanding how dark matter behaves within and around supervoids remains an active area of research, offering clues about its nature and properties. Another important factor is dark energy, the mysterious force driving the accelerated expansion of the universe. While gravity works to pull matter together, dark energy pushes space apart, influencing how structures evolve over time. In regions of low density, such as voids, the effects of dark energy can become more pronounced, contributing to the expansion of these regions. This interplay between gravity and dark energy adds another layer of complexity to the story of how voids form and grow. Returning to the early universe, it is fascinating to consider that the seeds of these vast empty regions were present almost from the beginning. The cosmic microwave background, the faint afterglow of the Big Bang, provides a snapshot of the universe when it was only about 380,000 years old. Detailed measurements of this radiation reveal the tiny density fluctuations that would later evolve into the structures we see today. In these patterns, we can see the faint outlines of future filaments and voids, a kind of blueprint for the cosmic web. As time progressed, the universe cooled and matter began to clump together more effectively. Gas condensed into the first stars and galaxies, lighting up the cosmos. Meanwhile, the underdense regions continued to lose matter, becoming increasingly empty. the contrast between dense and empty regions grew more pronounced, giving rise to the large-scale structure that now defines the universe. The growth of voids is not simply a matter of expansion. It also involves the movement of matter along the filaments of the cosmic web. Galaxies and gas flow toward denser regions, leaving behind the voids. This flow is influenced by gravitational gradients, with matter naturally moving from areas of lower density to areas of higher density. Over billions of years, this process effectively evacuates the voids, making them larger and emptier. Interestingly, the interiors of voids can also contain smaller structures. While they are defined by their low density, they are not completely devoid of matter. Small filaments, isolated galaxies, and diffuse gas can still be found within them. These features are often remnants of the initial density fluctuations, surviving within the expanding void. Studying these structures provides insights into the early stages of cosmic evolution and the processes that govern the distribution of matter. The concept of a void's birth, then, is not a single event, but a continuous process. It begins with tiny fluctuations in the early universe, evolves through the gradual movement of matter, and continues as the universe expands. Even today, supervoids are still growing, their boundaries shifting as matter flows outward. This ongoing evolution means that the universe's large-scale structure is not fixed, but dynamic, changing slowly over time. Considering this process on human timescales can feel almost impossible. The changes occur over billions of years, far beyond the span of any individual life or even the entire history of human civilization. Yet, through observation and simulation, we can reconstruct this history, piecing together the story of how the universe transformed from a nearly uniform state into the richly structured cosmos we observe today. There is something quietly profound in this transformation. From tiny fluctuations, almost imperceptible differences in density, have emerged structures of immense scale, including both the densest clusters and the emptiest voids. The universe did not require dramatic events to create these features. Instead, it relied on the steady, consistent action of physical laws, applied over vast stretches of time. This perspective invites a different way of thinking about emptiness. Supervoids are not gaps that were carved out suddenly or violently. They are the natural result of matter gathering elsewhere, leaving behind regions that gradually became emptier. Their birth is tied to the same processes that created galaxies and stars, making them an integral part of the universe's evolution. As this understanding settles in, the idea of a void becomes less about absence and more about process. It is a region shaped by the flow of matter, the pull of gravity, and the expansion of space. It is defined not only by what is missing, but by how that absence came to be. And in that sense, the birth of a void is as much a story of creation as the formation of a galaxy or a star. Beneath the idea of emptiness, there is a subtle truth that often goes unnoticed. Even in the most desolate regions of the universe, even in the deepest interiors of supervoids, there is still something present. Not much, not nearly enough to resemble the bustling structure of galaxies or clusters, but not absolute nothing either. What we call empty space is, in reality, a quiet mixture of faint ingredients, scattered so thinly that their presence is almost imperceptible. And it is here, within this barely there landscape, that the notion of a dark heart begins to take shape. At first glance, a supervoid seems like the closest thing the universe offers to true nothingness. Galaxies are rare, sometimes separated by tens or even hundreds of millions of light years. Bright stars, glowing nebulae, and dense clusters simply do not populate these regions in any meaningful way. But when astronomers examine these spaces more carefully, they find that emptiness is never complete. There is always a faint residue, a whisper of matter and energy that lingers even in the most isolated corners. One of the most important components hidden within supervoids is dark matter. Unlike ordinary matter, which interacts with light and can be observed directly, dark matter remains invisible. It does not emit, absorb, or reflect light, making it extraordinarily difficult to detect. Yet its gravitational influence is unmistakable. It shapes the motion of galaxies, bends light travelling across vast distances, and provides the underlying framework for the cosmic web itself. Inside supervoids, dark matter is present, but in much lower concentrations than in filaments or clusters. It is spread thinly, like a faint mist stretched across an enormous volume. Even though it is sparse, it still contributes to the overall structure of the void, influencing how the region evolves over time. Its presence ensures that even the emptiest places in the universe are not entirely devoid of substance. Instead, they are filled with a subtle, nearly invisible scaffolding that quietly holds everything together. Alongside dark matter, there is also diffuse gas, primarily hydrogen, drifting through these regions. This gas is extremely tenuous, far less dense than even the best vacuums we can create on Earth. If you were to gather all the particles in a typical cubic meter of a supervoid, you might find only a handful of atoms. And yet, across the immense scale of a void, even this sparse distribution adds up to a measurable presence. The gas does not form stars easily, nor does it clump into visible structures, but it exists, contributing to the faint background of matter that permeates space. There are also occasional galaxies, though they are few and far between. These galaxies tend to be smaller, less luminous, and more isolated than those found in denser regions. Their evolution is quieter, less influenced by interactions or mergers. They drift through the void with little disturbance, following paths shaped primarily by the overall expansion of the universe rather than by close gravitational encounters. In a sense, they are the loneliest galaxies of all, existing in environments where neighbours are so distant that interaction becomes a rare event over cosmic timescales. Radiation, too, passes through these regions. The cosmic microwave background fills all of space, including supervoids, providing a faint, nearly uniform glow that originates from the early universe. This radiation is incredibly subtle, detectable only with sensitive instruments, yet it serves as a reminder that even the emptiest regions are connected to the universe's origin. Light from distant galaxies also traverses these voids, travelling vast distances with minimal interference, carrying information across the cosmos. Considering all of this, the phrase "dark heart of nothing" begins to feel less like a contradiction and more like a description of balance. The heart of a supervoid is not empty in the absolute sense, but it is as close as the universe comes to that idea. It is a place where matter is reduced to its faintest traces, where structure is minimal, and where the usual markers of cosmic activity fade into the background. There is an interesting consequence of this near emptiness. In regions where matter is dense, gravity plays a dominant role, shaping the motion of objects and the flow of time in subtle ways. In a supervoid, with far less matter present, gravity's influence is weaker. This creates an environment where the expansion of the universe becomes more noticeable, where space itself stretches with fewer interruptions. It is not that time behaves differently in a direct perceptible way, but the balance of forces shifts, giving the void a distinct character compared to denser regions. Light travelling through a supervoid experiences this difference. Without strong gravitational fields to pull it inward or alter its path significantly, light moves more freely. However, as it crosses these regions, it can lose a tiny amount of energy due to the expansion of space, leading to slight changes in its wavelength. These effects are incredibly small yet measurable, offering another way for astronomers to detect and study the presence of voids. From a more reflective perspective, the idea of something existing within nothingness challenges our usual way of thinking. We tend to imagine emptiness as a complete absence, a blank canvas with nothing to observe or measure. But the universe does not operate in such absolute terms. Even its emptiest regions contain faint traces of matter and energy, subtle influences that persist despite the overwhelming sense of absence. The dark heart is not a void in the strictest sense, but a region where everything has been stretched to its limits, where presence is reduced to its most delicate form. This realization brings a certain calmness to the concept. The emptiness is not hostile or threatening. It is quiet, stable, and persistent. It does not demand attention or produce dramatic events. Instead, it simply exists, a vast expanse where the universe continues its slow, steady evolution. The faint matter within it drifts, the background radiation hums softly, and the distant galaxies maintain their quiet journeys. It is also worth considering how these regions fit into the larger picture of the universe. Supervoids are not isolated anomalies. They are integral parts of the cosmic web, connected to filaments and clusters, influencing and being influenced by the distribution of matter around them. The dark matter within them, though sparse, is part of the same network that shapes the entire cosmos. The gas, the radiation, the occasional galaxies, all are pieces of a larger system that extends across billions of light years. The term dark heart can also be understood in a metaphorical sense. It suggests something hidden, something not immediately visible, yet fundamentally important. In supervoids, what is hidden is not a dense object or a powerful force, but the subtle presence of almost nothing. It is the quietest expression of the universe's complexity, a reminder that even absence can have structure and influence. Imagining yourself within such a region once again, the experience would not be one of complete darkness or silence, but of minimal variation. The few galaxies present would appear distant and faint. The background radiation would be uniform and subtle. There would be no dramatic shifts, no sudden changes in environment. Instead, there would be a sense of continuity, a steady state where the universe unfolds at its most understated pace. This kind of environment invites a different kind of observation. Without the distractions of dense structures, it becomes easier to notice the small details, the subtle patterns, the faint signals that might otherwise be overlooked. For astronomers, supervoids provide a unique laboratory, a place where the influence of certain forces can be studied in isolation, without the complexity introduced by dense regions. At the same time, these regions highlight the limits of our understanding. While we can detect dark matter through its gravitational effects, we still do not know exactly what it is. While we can measure the expansion of the universe, the nature of dark energy remains uncertain. Supervoids, with their sparse content and subtle influences, sit at the intersection of these mysteries, offering clues while also raising new questions. Allowing these ideas to settle, the notion of emptiness becomes less unsettling and more intriguing. The dark heart of nothing is not a place of absence in the strictest sense, but a region where the universe reveals its most delicate balance. Matter, energy, and space itself are present, but in their most diluted forms, stretched across unimaginable distances. Long before galaxies gathered into clusters or stretched themselves into filaments, before supervoids expanded into the vast regions we've been imagining, the universe existed in a state that was far more uniform than anything we see today. It was hot, dense, and filled with a glowing sea of particles and radiation, all interacting constantly. There were no empty regions yet, no cosmic web, no quiet giants. And yet, hidden within that early uniformity were the faintest traces of difference, tiny variations that would eventually grow into everything we now observe, including the immense supervoids that define the loneliest regions of space. These early traces are what we now call the echoes of the Big Bang. They are not sounds in the traditional sense, but patterns imprinted in the fabric of the universe itself. The most direct evidence of these echoes comes from something known as the cosmic microwave background, often abbreviated as the CMB. This faint radiation fills all of space, reaching us from every direction, and it represents the oldest light we can observe, a snapshot of the universe when it was only about 380,000 years old. At that time, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, light could not travel freely because it was constantly scattered by charged particles. But once neutral atoms formed, the universe became transparent, allowing light to move unimpeded. That light has been travelling ever since, stretched by the expansion of the universe into the microwave wavelengths we detect today. When scientists map the cosmic microwave background, they do not see a perfectly uniform glow. Instead, they observe tiny temperature variations, differences of just a few millionths of a degree. These variations correspond to the slight differences in density that existed in the early universe. Some regions were a bit denser, some a bit less so. These small fluctuations are the seeds from which all large-scale structure grew. In those slightly denser regions, gravity would eventually pull matter together, forming the filaments and clusters of galaxies. In the slightly less dense regions, matter would drift away, leaving behind the beginnings of voids. Over billions of years, these initial differences would be amplified, transforming into the vast cosmic web we see today, with its intricate network of structures and its enormous empty spaces. Supervoids, then, are not late additions to the universe. Their origins can be traced directly back to these early fluctuations. The regions that would become supervoids were already underdense in the infant universe, even if the difference was incredibly small. As time passed, gravity and expansion worked together to exaggerate these differences, gradually turning slight deficits of matter into the immense empty regions we now observe. One of the most intriguing aspects of this connection is how supervoids can still leave an imprint on the cosmic microwave background, even billions of years after the Big Bang. When light from the CMB passes through a supervoid, it experiences subtle changes. Because the void has less gravitational pull than surrounding regions, the light does not gain as much energy when entering and exiting it. Combined with the ongoing expansion of the universe, this results in a slight cooling effect in the observed radiation. This effect is extremely small, but it is measurable with sensitive instruments. It provides a way for astronomers to detect supervoids indirectly, by looking for these tiny variations in the background radiation. In this sense, supervoids do not just arise from the echoes of the Big Bang, they also contribute to them, leaving their own faint signatures imprinted on the oldest light in the universe. The cold spot mentioned earlier is one of the most famous examples of this phenomenon. It is a region of the cosmic microwave background that appears slightly cooler than its surroundings. One possible explanation is that a large supervoid lies along the line of sight, affecting the energy of the light passing through it. While the exact cause of the cold spot is still debated, its existence highlights the connection between large-scale structures and the ancient radiation that fills the universe. Thinking about this relationship brings a different perspective to the idea of emptiness. Supervoids are not just gaps that formed later in cosmic history. They are deeply connected to the universe's beginnings, shaped by the same processes that created galaxies and stars. The echoes of the Big Bang are not just distant remnants. They are active participants in the ongoing story of the universe, influencing and reflecting the structures that have developed over billions of years. There is also a certain elegance in how these connections span such vast scales of time and space. The tiny fluctuations in the early universe, almost imperceptible differences in density, have grown into structures that span hundreds of millions of light years. The light that left those early moments still travels through these structures, carrying information about both the past and the present. It is a continuous thread, linking the beginning of the universe to its current state. From a more contemplative standpoint, this continuity invites a sense of perspective. The universe is not a collection of isolated events or structures, but a connected system where past and present are intertwined. The supervoids we imagine as vast empty spaces are, in fact, part of a story that began nearly 14 billion years ago. Their emptiness is not an absence of history, but a direct result of it. Even the way we observe these phenomena reflects this connection. Telescopes and detectors capture light that has travelled for billions of years, allowing us to see the universe as it was long ago. When we study the cosmic microwave background, we are looking back to a time before galaxies existed. When we map supervoids, we are observing the outcome of processes that began in that early era. The two are linked, different stages of the same unfolding narrative. There is something quietly reassuring about this continuity. The universe, despite its vastness and complexity, follows patterns that can be traced and understood. The same physical laws that governed the early fluctuations continue to shape the cosmos today. Gravity, expansion, and the behavior of matter and energy all work together in a consistent way, producing structures that evolve over time but remain connected to their origins. At the same time, these connections highlight the limits of our understanding. While we can measure the fluctuations in the cosmic microwave background with incredible precision, we still do not fully understand all the processes that influence them. The nature of dark matter and dark energy, the exact mechanisms that shaped the early universe, and the full implications of these structures are still subjects of ongoing research. Supervoids, with their subtle influence on the CMB, sit at the intersection of these mysteries. Returning to the idea of echoes, it is interesting to think of the universe as carrying a kind of memory. The patterns imprinted in the cosmic microwave background are like a record of the universe's earliest moments, preserved and stretched across space. Supervoids, in turn, are part of how that memory has evolved, shaped by billions of years of cosmic history. They are both a result of the past and a contributor to the present, a quiet reflection of the universe's long journey from uniformity to complexity. The emptiness of supervoids feels less like a void in the narrative and more like a continuation of it. They are not interruptions or gaps, but integral parts of the cosmic story, connected to the earliest moments and still influencing what we observe today. The faint glow of the cosmic microwave background passes through them, altered in subtle ways, carrying with it the imprint of both the beginning and the present. Finding something that is defined mostly by absence might sound like an impossible task. After all, how do you detect what isn't there? How do you measure emptiness across distances so large that even light takes millions of years to travel through them? And yet, this is exactly what astronomers have learned to do. Supervoids, despite their quiet nature, leave behind patterns, traces, and subtle effects that allow us to map them with surprising precision. Rather than looking for objects, scientists begin by looking for patterns. The key idea is simple. If you can map where galaxies are, you can also infer where they are not. Over the past few decades, enormous surveys of the sky have catalogued the positions of millions of galaxies, each one carefully measured in terms of its location and distance from Earth. These surveys create vast three-dimensional maps of the universe, revealing not just isolated points of light, but the overall distribution of matter across cosmic scales. When these maps are analysed, something remarkable appears. Galaxies are not scattered randomly. Instead, they cluster along filaments and nodes, forming the cosmic web we explored earlier. And between these structures, there are large regions where galaxies are scarce. These regions, when they reach sufficient size and low density, are identified as supervoids. In this way, emptiness is detected not directly, but through contrast. It is the absence of galaxies within a defined volume that reveals the presence of a void. The process, however, is more complex than simply spotting empty patches. Astronomers must account for observational limits, such as how faint a galaxy can be before it becomes undetectable, or how dust and other factors might obscure parts of the sky. Advanced statistical methods are used to ensure that what appears to be a void is not simply a gap in the data. By carefully analysing galaxy density across large regions, scientists can identify true underdense areas and measure their size, shape, and location. Distance plays a crucial role in this mapping. Knowing where a galaxy appears in the sky is only part of the picture. To understand the structure of the universe, astronomers also need to know how far away each galaxy is. This is typically done using redshift, the stretching of light to longer wavelengths as the universe expands. The greater the redshift, the farther away the galaxy is. By combining position and redshift data, researchers can construct a three-dimensional view of the cosmos, revealing the full extent of filaments, clusters, and voids. Once these maps are created, algorithms scan them for regions of low density. These algorithms identify areas where the number of galaxies falls significantly below the cosmic average, marking them as void candidates. Further analysis refines these detections, determining whether a region qualifies as a supervoid based on its size and depth. The result is a catalogue of vast empty spaces, each one mapped and measured despite containing very little to observe directly. Another method of detecting supervoids involves observing how they affect light passing through them. As we touched on earlier, light travelling across the universe does not move in isolation. It is influenced by the distribution of matter and energy along its path. In dense regions, gravity can bend light, creating distortions known as gravitational lensing. In supervoids, the opposite effect occurs. With less mass present, there is less gravitational influence, leading to subtle differences in how light propagates. One of the most important effects in this context is the integrated Sachs-Wolf effect. As light from the cosmic microwave background passes through a supervoid, it experiences a slight change in energy due to the expansion of space and the lack of strong gravitational fields. This results in a tiny temperature difference in the observed radiation. By comparing maps of the cosmic microwave background with maps of galaxy distribution, scientists can identify correlations that point to the presence of supervoids. This method is particularly valuable because it provides an independent way to detect voids, complementing galaxy surveys. Even if a region contains very few visible galaxies, its influence on background radiation can still reveal its existence. In this sense, supervoids become visible through their effects, rather than through direct observation. There are also techniques that involve studying the motion of galaxies. In regions of varying density, galaxies do not simply move with the expansion of the universe. They also experience what are known as peculiar velocities, motions caused by gravitational interactions. Near a supervoid, galaxies tend to move away from the void center, drawn toward denser regions. By analysing these motions, astronomers can infer the presence of underdense areas and map their influence on surrounding structures. Computer simulations play an essential role in all of this. By recreating the evolution of the universe from its earliest moments, scientists can predict where voids should form and how they should behave. These simulations incorporate the effects of gravity, dark matter, and dark energy, producing virtual universes that can be compared with observations. When the simulated structures match what we see in real data, it strengthens our confidence in the models and helps refine our understanding of cosmic evolution. Detecting supervoids is therefore not a single process, but a combination of approaches. Galaxy surveys provide the primary map. Statistical analysis identifies underdense regions, background radiation reveals subtle imprints, and galaxy motions offer additional clues. Together, these methods allow scientists to piece together a picture of something that cannot be seen directly. There is something quietly remarkable about this approach. It shows that absence can be studied just as rigorously as presence. In everyday life, we tend to focus on what we can observe directly, what we can touch or measure. In cosmology, however, the gaps between objects can be just as informative as the objects themselves. Supervoids remind us that understanding the universe requires looking not only at what is there, but also at what is missing. The precision of these measurements continues to improve. New surveys, more powerful telescopes, and advanced computational techniques are expanding our ability to map the universe in greater detail. As more galaxies are catalogued and more data is collected, the structure of the cosmic web becomes clearer, and the boundaries of supervoids are defined with increasing accuracy. At the same time, these efforts reveal new questions. Some supervoids appear larger or deeper than expected, challenging existing models. Others may be connected in ways that are not yet fully understood, forming networks of emptiness within the larger cosmic web. Each new discovery adds complexity to the picture, reminding us that even in the study of nothingness, there is always more to learn. Reflecting on this process, it becomes clear that detecting the invisible is as much about interpretation as it is about observation. The data itself does not label regions as voids or filaments. It is through careful analysis, comparison, and modelling that patterns emerge. Scientists must distinguish between true emptiness and apparent gaps, between meaningful structures and random variations. This requires both precision and creativity, a combination of rigorous methods and imaginative thinking. There is a certain calm in the realization that even the most elusive aspects of the universe can be understood with patience and care. Supervoids may not shine or emit signals in the way galaxies do, but they are not beyond our reach. Through indirect observation, through the careful study of patterns and effects, we can map these vast regions and begin to understand their role in the cosmos. Somewhere in the vast glow of the oldest light in the universe, there is a patch that doesn't quite fit. It doesn't stand out dramatically at first glance. There are no sharp edges, no obvious boundaries, nothing that immediately signals something unusual. And yet, when scientists map the cosmic microwave background with great precision, this region reveals itself as slightly cooler than its surroundings. Not by much, only a fraction of a degree, but enough to raise questions that have lingered for years. This is what has come to be known as the cold spot, and it has become one of the most intriguing puzzles connected to supervoids. The cosmic microwave background, as we've explored, is remarkably uniform. It represents the afterglow of the Big Bang, stretched across the universe and visible in every direction. The tiny variations in temperature that appear in this background are expected, and they match the predictions of our cosmological models. These variations reflect the early density fluctuations that eventually led to galaxies, clusters, and voids. Most of these fluctuations are small and random, fitting neatly within our understanding of how the universe evolved. The cold spot, however, is different. It is larger than typical fluctuations and slightly colder than what standard models would predict. This does not mean it is dramatically out of place, but it is unusual enough to attract attention. Its existence raises a simple but compelling question. What could cause such a feature in an otherwise well-understood pattern? One of the leading explanations brings us back to the quiet giants we've been exploring. The idea is that a massive supervoid lies between us and the region of the cold spot. As light from the cosmic microwave background travels through this enormous underdense region, it loses a small amount of energy due to the expansion of space. Without strong gravitational fields to counteract this effect, the photons emerge slightly cooler than they would otherwise be. Over the vast scale of a supervoid, this tiny effect can accumulate, producing a measurable difference in temperature. This explanation is appealing because it connects two seemingly separate phenomena: the large-scale structure of the universe and the ancient radiation that fills it. It suggests that supervoids are not just passive features, but active participants in shaping what we observe, even when it comes to the oldest light in existence. The cold spot, in this view, is not an anomaly in the early universe, but a result of structures that formed much later, imprinting themselves on that ancient radiation as it travelled across billions of light years. Yet, as with many things in cosmology, the situation is not entirely straightforward. While there is evidence of a supervoid in the direction of the cold spot, measurements suggest that it may not be large or deep enough to fully account for the observed temperature difference. This leaves room for other possibilities, and scientists have explored a range of alternative explanations. One possibility is that the cold spot is simply a statistical fluctuation. Given the vast number of temperature variations in the cosmic microwave background, it is not impossible for an unusually large or cold region to appear by chance. In this case, the cold spot would not require any special explanation beyond the inherent randomness of the early universe's fluctuations. It would be rare, but not impossible, a reminder that even well-understood systems can produce outliers. Another idea is that the cold spot could be linked to more exotic physics. Some theories suggest that it might be evidence of a feature from the early universe that does not fit within the standard model of cosmology. Others have proposed connections to concepts like cosmic textures, hypothetical defects in space-time that could have formed during phase transitions in the early universe. These ideas are more speculative, but they highlight how a single observation can open the door to entirely new ways of thinking about the cosmos. There is even a more imaginative possibility, one that has captured public attention, though it remains highly speculative. Some have suggested that the cold spot could be evidence of a collision between our universe and another, a kind of imprint left behind by an encounter with a neighbouring cosmos. While this idea belongs more to the realm of theoretical exploration than established science, it illustrates how deeply intriguing the cold spot is, prompting questions that reach beyond the boundaries of our current understanding. Returning to the more grounded explanations, the connection between supervoids and the cold spot remains one of the most actively studied. Astronomers continue to refine their measurements, mapping the distribution of galaxies in that region with increasing detail. By understanding the size, shape, and density of the void, they hope to determine whether it can fully explain the observed temperature difference, or whether additional factors must be involved. What makes this mystery particularly compelling is its subtlety. There is no dramatic event, no explosion or collapse, no sudden shift in the structure of the universe. Instead, there is a faint variation in temperature, a slight deviation from expectation, detected only through careful observation and precise measurement. And yet, this small difference carries significant implications, touching on the nature of cosmic structure, the behaviour of light over vast distances, and the fundamental processes that shape the universe. Considering this, the cold spot becomes more than just an anomaly. It becomes a point of connection, linking the earliest moments of the universe to its current large-scale structure. The light we observe today has travelled for billions of years, passing through countless regions of varying density. Along the way, it has been subtly altered, carrying with it a record of the structures it encountered. The cold spot is one such record, a faint imprint of something that lies between us and the edge of the observable universe. There is also a certain elegance in how this mystery unfolds. The universe does not present its secrets in obvious ways. Instead, it offers hints, small deviations, patterns that invite closer inspection. The cold spot is one of those hints, encouraging scientists to look deeper, to question assumptions, and to explore the connections between different aspects of cosmology. From a broader perspective, this kind of investigation reflects the nature of scientific inquiry itself. Observations lead to questions, questions lead to hypotheses, and hypotheses are tested through further observation and analysis. Sometimes the answers confirm our expectations, reinforcing our understanding. Other times, they reveal gaps or inconsistencies, pointing toward new directions of research. The cold spot sits at this intersection, a feature that is understood in part but not completely, inviting continued exploration. The idea of a supervoid influencing the oldest light in the universe becomes less surprising and more natural. The universe is interconnected on scales that stretch far beyond everyday experience. Structures formed billions of years after the Big Bang can still affect the light that originated in those earliest moments. The passage of time and the expansion of space weave these connections together, creating a continuous narrative that spans the entire history of the cosmos. And with that in mind, it becomes clear that supervoids are not isolated features, but part of a larger system where gravity, light, and expansion interact in subtle and complex ways. It might seem, at first thought, that gravity would have very little to do in a place defined by emptiness. After all, gravity is what pulls things together, what shapes galaxies, binds stars and gathers matter into dense clusters. In a supervoid, where matter is scarce and distances are immense, you might expect gravity to simply fade into irrelevance. And yet, even here, even in the quietest regions of the universe, gravity is still present, still shaping motion, still guiding the slow and steady evolution of everything within and around these vast spaces. The difference is not that gravity disappears, but that it becomes subtle. In dense regions, its influence is obvious. Galaxies orbit each other, clusters hold together, and light bends as it passes near massive objects. In a supervoid, gravity works more like a gentle suggestion than a firm command. It does not pull strongly inward toward a central point because there is no central mass to dominate the region. Instead, its influence is spread out, coming mostly from the surrounding structures, the filaments and clusters that lie beyond the void's edges. Imagine standing in a wide open landscape with hills far in the distance. You would not feel a strong pull in any particular direction, but if you waited long enough, you might notice a slow drift, a gradual movement guided by the distant terrain. That is somewhat similar to how gravity behaves inside a supervoid. The few galaxies that exist there are not strongly bound to each other. Instead, they feel a weak tug from the denser regions outside, slowly guiding their motion over immense periods of time. This outward pull is one of the key reasons supervoids grow. Matter within a void is gently drawn toward the surrounding filaments, leaving the interior increasingly empty. The process is not dramatic. There are no sudden evacuations or rapid flows. It is a slow migration, unfolding over billions of years, where galaxies and gas drift outward, contributing to the overall expansion of the void. Gravity, in this sense, is not just shaping what gathers together, but also what spreads apart. The boundaries of a supervoid are where this influence becomes more noticeable. As you move from the interior toward the edges, the density of matter gradually increases. Gravity becomes stronger, more directional, guiding galaxies into the filaments that define the cosmic web. These edges are not sharp borders, but transitional regions where the balance between emptiness and structure shifts. Galaxies near these boundaries often experience a more complex set of gravitational influences, pulled in multiple directions as they respond to nearby clusters and filaments. One of the most interesting consequences of this gentle gravitational landscape is how it affects motion on large scales. In cosmology, the movement of galaxies is often described in terms of both the expansion of the universe and their peculiar velocities, the additional motion caused by gravitational interactions. Inside a supervoid, peculiar velocities tend to be directed outward, away from the center of the void. This creates a kind of large-scale flow, where matter is gradually redistributed from underdense regions to denser ones. These flows are incredibly slow by everyday standards, but over cosmic timescales, they are significant. They contribute to the formation of the cosmic web, reinforcing the contrast between filaments and voids. Gravity, even in its gentlest form, acts as a sculptor, shaping the distribution of matter not through forceful action, but through persistent influence. There is also a connection between gravity and the way light behaves in these regions. While supervoids do not have the strong gravitational fields needed to produce dramatic lensing effects, they still influence the path of light in subtle ways. Photons travelling through a void experience less gravitational pull, which can lead to slight differences in their energy and trajectory compared to light passing through denser regions. These effects are small, but they are measurable, providing another way to study the influence of gravity in places where matter is scarce. In addition to shaping motion and light, gravity also plays a role in defining the overall structure of the universe. The cosmic web, with its filaments and voids, is a direct result of gravitational interactions over billions of years. Supervoids are not regions where gravity has failed, but regions where its effects have led to a redistribution of matter, creating large-scale patterns that reflect the balance between attraction and expansion. It is also worth considering how gravity interacts with dark energy in these regions. Dark energy, the force driving the accelerated expansion of the universe, becomes more prominent in areas of low density. In a supervoid, where there is less matter to counteract this expansion, the influence of dark energy is relatively stronger. This means that the expansion of space within and around voids can proceed slightly faster, further contributing to their growth. This interplay between gravity and dark energy adds another layer of complexity to the behaviour of supervoids. Gravity works to pull matter toward denser regions, while dark energy pushes space apart. In dense areas, gravity tends to dominate, keeping structures bound together. In underdense regions, dark energy has more freedom to act, allowing space to expand more rapidly. Supervoids, therefore, become regions where this balance shifts, where the influence of expansion becomes more noticeable. From a broader perspective, this balance highlights the dynamic nature of the universe. Even in the quietest regions, forces are at work, shaping the distribution of matter and energy. The absence of dramatic events does not mean the absence of activity. Instead, it reflects a different kind of activity, one that is slow, subtle, and spread across immense distances. Reflecting on this, the idea of gravity as a gentle hand becomes more fitting. It is not always a force that acts with intensity or urgency. Sometimes it works quietly, guiding motion over billions of years, shaping structures without drawing attention to itself. In supervoids, this gentle influence is especially apparent, revealing a side of gravity that is easy to overlook when focusing on more dramatic phenomena like black holes or galaxy collisions. Considering the experience of a galaxy within a supervoid, its motion would be guided by this gentle hand. There would be no strong pulls from nearby neighbours, no dramatic interactions. Instead, its path would be influenced by distant structures, its trajectory slowly adjusting as it responds to the broader gravitational landscape. Over time, it might drift toward the edges of the void, joining the filaments where matter is more concentrated. This slow movement also affects how structures evolve within and around voids. Galaxies that remain within the interior tend to evolve in relative isolation, while those near the edges may eventually become part of larger clusters. The gentle gravitational flows contribute to this process, guiding matter along the pathways defined by the cosmic web. There is a certain calmness in this picture. The universe is not always a place of violent events and rapid changes. Much of its evolution occurs through slow, steady processes that unfold over vast stretches of time. Supervoids, with their sparse matter and subtle gravitational influences, are a clear example of this quieter side of cosmic evolution. As these ideas settle, the emptiness of supervoids begins to feel less like an absence of activity and more like a different kind of environment, one where forces still operate but in a more understated way. Gravity is still present, still shaping motion and structure, but it does so with a light touch, guiding rather than commanding. Somewhere between the deep quiet of a supervoid and the crowded activity of the cosmic web, there is a region that feels like a threshold. Not a sharp boundary, not a clear line you could draw across space, but a gradual shift where emptiness begins to give way to structure. This is where galaxies live on the edge, caught between two very different environments, influenced by both the calm interior of the void and the stronger gravitational pull of the surrounding filaments. In these transitional regions, the density of matter begins to increase, though not suddenly. A galaxy drifting outward from the centre of a void does not cross a border and suddenly find itself surrounded by neighbours. Instead, the change is subtle. Over millions of light years, the number of nearby galaxies slowly grows. Distances between them shrink, gravitational influences strengthen, and the quiet isolation of the void begins to soften. Galaxies in these edge regions experience a unique set of conditions. They are not as isolated as those deep within the void, but they are also not as tightly bound as those in dense clusters. This balance gives them a kind of independence. Their evolution is shaped partly by their internal processes and partly by the growing influence of their surroundings. It is a place where subtle changes can have long-term consequences. One of the most noticeable differences is the increase in gravitational interaction. As galaxies approach the edges of a void, they begin to feel stronger pulls from nearby filaments and clusters. These forces can alter their trajectories, gradually redirecting their motion toward denser regions. Over time, many of these galaxies will leave the void entirely, becoming part of the larger structures that define the cosmic web. This movement is not abrupt. It unfolds slowly, guided by the same gentle gravitational flows we explored earlier. A galaxy may spend billions of years drifting through the outer layers of a void before finally joining a filament. During this time, its environment changes gradually, influencing everything from its structure to its rate of star formation. Star formation itself can be affected by this transition. In the deep interior of a void, galaxies often have limited access to fresh gas, which can slow the creation of new stars. As they move toward denser regions, they may encounter more material, either through interactions with other galaxies or through the gas that flows along filaments. This can lead to an increase in star formation, changing the galaxy's appearance and activity over time. There is also the possibility of interactions and mergers, though these remain less common than in dense clusters. In edge regions, galaxies are still relatively far apart, but close enough that occasional encounters can occur. When they do, these interactions can reshape galaxies, triggering bursts of star formation or altering their structure. Compared to the chaotic environments of galaxy clusters, these events are rare and gentle, but they still play a role in the long-term evolution of galaxies on the edge. The shape and orientation of galaxies can also reflect their position within the cosmic web. Observations suggest that galaxies near filaments often align with the structure of the web itself, their spins and orientations influenced by the flow of matter along these visual threads. In edge regions, this alignment begins to emerge as galaxies transition from the more random orientations found in the void interior to the more structured patterns seen in filaments. Another subtle effect involves the distribution of dark matter. As galaxies approach the edges of voids, they move into regions where dark matter is more concentrated. This changes the gravitational environment, influencing the motion of stars within galaxies and the behavior of surrounding gas. The increased presence of dark matter helps stabilize structures, allowing galaxies to grow and evolve in ways that are less common in the sparse interior of a void. From a larger perspective, these edge regions are where the cosmic web becomes most apparent. If you could map the distribution of galaxies across a vast volume of space, you would see the density gradually increase toward the filaments, forming a pattern that connects clusters across enormous distances. The edges of voids are not just boundaries, but part of a continuous structure, linking the emptiness of the void to the richness of the web. Imagining a journey through this region offers a sense of transition. Starting from the deep interior of a supervoid, you would first notice only distant, faint galaxies. As you travel outward, those galaxies would become more frequent. The darkness would still dominate, but it would be punctuated by more points of light. Eventually, the structure of the web would begin to emerge, with galaxies forming loose chains that hint at the filaments beyond. This gradual change can feel almost like moving from open ocean toward a coastline. At first, there is only vast water, stretching in all directions. Then, slowly, signs of land begin to appear. The water becomes shallower, the horizon more varied, until finally the shoreline comes into view. In the universe, this shoreline is not a solid boundary, but a region where matter becomes more concentrated, where the influence of the cosmic web grows stronger. There is something quietly fascinating about these in-between places. They are neither empty nor crowded, neither isolated nor connected. They exist in a state of balance, influenced by both sides of the cosmic structure. This balance makes them particularly valuable for studying how galaxies evolve, offering insights into how environment shapes the development of cosmic structures. Astronomers pay close attention to these regions for this reason. By comparing galaxies in void interiors, edge regions, and dense clusters, they can identify patterns and differences that reveal the role of environment in shaping galaxies. These studies help answer questions about why galaxies have different shapes, sizes, and rates of star formation, and how these properties change over time. The edges of voids also play a role in the larger dynamics of the universe. They are regions where matter flows, where gravitational forces guide the movement of galaxies along the filaments. This flow contributes to the overall structure of the cosmic web, reinforcing the connections between clusters and shaping the distribution of matter across vast distances. At the same time, these regions remind us that the universe does not operate in extremes alone. While supervoids and dense clusters represent opposite ends of the spectrum, much of the universe exists in between. The edges of voids are part of this middle ground, where gradual changes create a continuum rather than a sharp divide. Considering this, the idea of loneliness takes on a slightly different meaning. Galaxies on the edge are not as isolated as those deep within a void, but they still experience a level of separation that is difficult to imagine. Their nearest neighbours may still be millions of light years away, yet they are part of a larger structure, connected through the filaments of the cosmic web. This balance between isolation and connection reflects a broader theme in the universe. Structures are not defined solely by their extremes, but by the transitions between them. The edges of voids are where these transitions occur, where the quiet emptiness begins to give way to the intricate patterns of the cosmic web. Letting this picture settle, the universe begins to feel less like a collection of separate regions and more like a continuous landscape, where emptiness and structure blend into each other. The boundaries are not rigid, but fluid, shaped by the slow movement of matter and the gentle influence of gravity. Try for a moment to let go of clocks. No ticking seconds, no glowing numbers on a screen, no schedule quietly waiting in the background. Just space, stretching in every direction, and within it, one of these immense supervoids we've been exploring. In a place like that, where galaxies are rare and distances are vast beyond ordinary imagination, the idea of time begins to feel a little different, not because time itself changes in a dramatic way, but because everything we use to measure it becomes sparse, distant, and almost irrelevant. On Earth, time is anchored to repetition. The rotation of the planet gives us day and night. The orbit around the sun marks the passing of years. Our bodies follow rhythms, sleep and wake cycles, heartbeats, breaths. Even in space, aboard spacecraft or orbiting stations, astronauts rely on artificial schedules to maintain a sense of order. Time, in our daily lives, is tied closely to events, to change, to cycles that repeat with comforting regularity. Inside a supervoid, those familiar anchors fade. There is no nearby star rising and setting across a horizon. There are no neighbouring galaxies close enough to offer a sense of motion or change over short time scales. The few galaxies that exist are so distant that their movement is imperceptible across generations, even across civilizations. In such a place, time is still passing exactly as it does everywhere else, but it becomes harder to feel it. From a physical perspective, time behaves according to the same laws we've already touched upon. Einstein's relativity tells us that time can stretch or compress depending on gravity and motion. Near massive objects like black holes, time slows noticeably. In regions with less gravity, like supervoids, time runs slightly faster relative to those dense areas. The difference, however, is incredibly small. You wouldn't notice it without precise instruments. Your watch would tick as usual. Your body would age as expected. And yet, even though the physical change is minimal, the experience of time in such a place would feel profoundly different. Without frequent events, without nearby interactions, without visible changes happening around you, time would seem to stretch. Moments would not be marked by activity, but by stillness. It is a bit like sitting in a quiet room where nothing changes for hours, The clock continues, but your sense of its passage becomes fluid, less defined. This brings us to an interesting distinction, one that has appeared before in our journey, between time as measured by physics and time as perceived by the mind. In a supervoid, physical time flows steadily, governed by the same universal laws. But psychological time, the way we interpret and feel its passage, would likely slow down dramatically. With fewer events to mark its progress, each moment might feel extended, open, almost unstructured. Consider how we already experience this on Earth. When you're waiting with nothing to occupy your attention, time can feel slow and drawn out. When you're engaged, busy or distracted, time seems to pass quickly. The difference lies not in the clock, but in your perception. In a supervoid, the environment itself encourages that slower perception. There is simply less happening to divide time into smaller, memorable segments. At the same time, there is another effect to consider, one tied not to perception, but to the universe's expansion. In underdense regions like supervoids, the expansion of space can proceed slightly more freely, with less resistance from gravitational attraction. Over billions of years, this leads to these regions growing larger, stretching further apart. This expansion subtly influences the flow of time on cosmic scales, not by changing its fundamental nature, but by altering the distances over which events occur. Light travelling through a supervoid takes longer to cross it as the space itself expands. Galaxies move farther apart, increasing the time it would take for signals or interactions to occur between them. In this way, the emptiness amplifies the separation not just in space, but in temporal connection. Events that might once have influenced each other become increasingly isolated as the void expands. This creates a kind of temporal isolation, not a change in how time flows locally, but a change in how events relate to one another across distance. In dense regions, galaxies can interact, merge, and influence each other over relatively shorter timescales. In a supervoid, those interactions are rare and separated by immense spans of time. Cause and effect on a cosmic level become more distant, more spread out. There is also a subtle connection to the arrow of time, the idea that time moves in a particular direction, from past to future, driven largely by the increase of entropy. In a supervoid, where matter is sparse and interactions are limited, the processes that increase entropy unfold differently. There are fewer collisions, fewer energetic exchanges, fewer events that rapidly increase disorder. The progression toward higher entropy still occurs, but it does so in a quieter, more gradual way. This does not mean time flows backward or becomes reversible. The arrow of time remains firmly pointed forward. But the rate at which noticeable changes occur can feel reduced. It is as though the universe, in these regions, is taking a slower, more measured approach to its ongoing evolution. From a more reflective angle, the relationship between time and emptiness invites a different kind of thought. We often think of time as something filled with events, something that is marked by change. But what happens when change becomes rare? When the environment offers very little to mark the passing of moments. In such cases, time begins to feel less like a sequence of events and more like a continuous, unbroken presence. This idea aligns with certain philosophical perspectives on time, where the distinction between moments becomes less important than the overall flow. In a supervoid, with its vast emptiness and minimal activity, time might feel less segmented, less divided into discrete units. Instead, it would stretch out, a continuous expanse much like space itself. There is also something calming about this concept. In our daily lives, time often feels compressed, divided into schedules, deadlines, and obligations. In contrast, the timescales of supervoids are so vast that urgency disappears. Events unfold over millions or billions of years. Changes happen slowly, almost imperceptibly. The universe, in these regions, is in no hurry. Of course, this perspective depends entirely on scale. For the universe, billions of years are simply part of its natural rhythm. For us, even a single lifetime is limited. Yet, by considering these immense spans, there is an opportunity to step back, to view time from a broader perspective, one where the usual pressures and constraints feel less immediate. Returning to the physical side, it is worth noting that the slight differences in gravitational influence within supervoids do contribute to measurable effects in timekeeping. Atomic clocks placed at different gravitational potentials will tick at slightly different rates. In principle, a clock deep within a supervoid would tick marginally faster than one in a dense cluster. The difference is extraordinarily small, but it is real. Another example of how even the quietest regions of the universe still follow the same fundamental laws. These subtle variations reinforce an important point. Time does not stop or disappear in emptiness. It continues, steady and consistent, shaped by the same physics that governs every part of the cosmos. What changes is not time itself, but the context in which it is experienced, the events that mark it, and the scale over which it unfolds. Allowing all of this to settle, the connection between time and emptiness becomes less abstract and more intuitive. In places where there is less matter, less interaction, and fewer events, time feels more open, more stretched. In places where there is more activity, more structure, and more change, time feels more segmented, more dynamic. Both experiences exist within the same universe, shaped by the same underlying laws. And as we continue this gentle exploration, it becomes natural to ask why these vast quiet regions, despite their calm and subtlety, are often described as some of the most unsettling places in the universe, and what it is about such immense emptiness that can make them feel more intimidating than even the most extreme cosmic objects. There is a particular kind of discomfort that does not come from danger, but from scale. It is not the sharp fear of something chasing you, nor the sudden shock of an unexpected event. Instead, it is quieter, slower, and more difficult to describe. It appears when the mind tries to grasp something too large, too empty, too far removed from everyday experience. Supervoids belong to that category. They are often called the scariest places in the universe, not because they are violent or destructive, but because of what they represent. When people think of frightening locations in space, the imagination usually turns to black holes. These are places where gravity is so strong that nothing, not even light, can escape. They bend space-time, distort reality, and present clear, dramatic risks. Supernovae, neutron stars, and gamma-ray bursts also come to mind, each associated with intense energy and catastrophic events. Supervoids are none of these things. They are not explosive, not energetic, not dangerous in a conventional sense, and yet they can feel more unsettling. The reason lies in how the human mind responds to emptiness. We are accustomed to environments filled with reference points. Even in the darkest night there are stars. Even in the most remote landscapes on Earth, there are sounds, textures, and boundaries. Our perception relies on contrast, on objects that define space and give us orientation. Remove those, and something shifts. The mind begins to search for structure and finds very little. Inside a supervoid, that absence becomes extreme. There are no nearby galaxies to anchor your sense of position. The distances between visible objects stretch beyond intuitive understanding. The sky, if viewed from within such a region, would appear unusually sparse, not completely dark, but lacking the richness and density we associate with the cosmos. The familiar patterns we use to make sense of space would be largely absent. This creates a kind of cognitive tension. The brain expects complexity and finds simplicity instead. It expects variety and finds uniformity. It expects proximity and encounters distance. This mismatch can lead to a feeling that is often described as eerie or unsettling, even though there is no immediate threat. Another aspect of this discomfort comes from the idea of isolation. On Earth, isolation is relative. Even in the most remote areas, there is still a sense that the rest of the world exists just beyond reach. Communication, travel, and connection are always possible, even if they require effort. In a supervoid, isolation is absolute on a scale that is difficult to comprehend. The nearest galaxy might be tens of millions of light-years away. Signals would take millions of years to travel. Interaction, in any meaningful sense, would be effectively non-existent. This level of separation challenges our usual understanding of connection. It suggests a place where influence is minimal, where cause and effect are stretched across enormous spans of time and space. It is not that nothing happens, but that everything happens slowly, quietly, and far apart. There is also the matter of scale itself. Supervoids are among the largest structures in the universe, not because they contain so much, but because they contain so little. Their size alone can be difficult to process. When you consider distances of hundreds of millions or even a billion light-years, the numbers lose their meaning. They become abstract, detached from any physical experience we can relate to. This abstraction contributes to the sense of unease. The mind prefers boundaries, limits, and definitions. Supervoids offer none of these in a familiar way. They are vast, diffuse, and open-ended. Their edges are not sharp, their interiors not uniform, and their scale not easily contained within a single idea. At the same time, there is something paradoxically calm about them. Unlike regions of intense activity, supervoids are stable. There are no sudden changes, no violent interactions, no unpredictable events. Their emptiness is consistent, their evolution slow. From a purely physical standpoint, they are among the least hazardous places in the universe. This contrast between safety and unease is what makes them particularly interesting. They do not threaten the body, but they challenge the mind. They force us to confront concepts that are outside our usual range of experience, such as near total emptiness, extreme isolation, and immense scale. The comparison with black holes highlights this difference. A black hole is frightening because of what it does. It pulls, compresses, and ultimately destroys anything that crosses its boundary. A supervoid, by contrast, does very little. It does not pull you in or push you away. It simply exists, vast and quiet. Yet, in some ways, that quietness can feel more profound. There is no clear boundary to approach, no event horizon to mark a transition. There is only an extended region where less and less is present, where the universe becomes increasingly sparse. It is a kind of gradual disappearance, not of matter entirely, but of density, structure, and interaction. Another factor is the absence of familiar cues. In dense regions of space, the presence of stars and galaxies provides a sense of direction and movement. In a supervoid, those cues are diminished. Without nearby reference points, it becomes harder to perceive motion or change. The environment feels static, even though the universe is still expanding and evolving. This lack of change can be disorienting. Humans are accustomed to environments where something is always happening, where time is marked by events. In a supervoid, the intervals between noticeable changes are so large that the environment feels almost timeless, even though time continues to pass. There is also a deeper, more abstract layer to this discomfort. Supervoids represent the idea that the universe is not uniformly filled with matter, that there are regions where very little exists. This challenges the intuitive notion that space, being vast, would naturally be full of things. Instead, it reveals that emptiness is a fundamental part of the cosmos, not an exception. For some, this realization can feel unsettling because it shifts perspective. It suggests that what we experience locally, a relatively dense and active region of space, is not representative of the universe as a whole. Instead, much of the cosmos is defined by emptiness, with structure concentrated in specific areas. At the same time, this perspective can also be calming. It places our own environment within a broader context, showing that the universe accommodates both complexity and simplicity. both activity and stillness. Supervoids are part of that balance, providing the space in which the cosmic web can exist. The notion of scariest places begins to feel less about danger and more about perception. Supervoids are not threatening in a physical sense. They do not harm or destroy. Their impact is psychological, arising from the way they stretch our understanding of space, distance, and connection. In this sense, they are mirrors of scale. They reflect back to us the limits of our imagination, the boundaries of what we can comfortably comprehend. They invite us to consider what it means for something to be vast, empty, and still part of the same universe we inhabit. If you were to place yourself in the middle of a supervoid and simply pause, not moving, not speaking, just existing within that immense stretch of space, the first thing you might notice is not what is there, but what is missing. There would be no wind, no distant hum, no subtle vibration travelling through the air because there is no air. There is no medium to carry sound, and in that sense the silence of a supervoid is not just quiet, it is absolute. On Earth, silence is never truly complete. Even in the quietest environments, there are always faint sounds, the movement of air, the distant shifting of objects, the subtle noise of life continuing in small ways. Our ears are accustomed to detecting these variations, and our brains are used to interpreting them as part of the background of existence. Silence, as we experience it, is relative. It is the absence of loud or noticeable noise, but not the absence of sound itself. In space, and especially in a supervoid, the situation is fundamentally different. Sound, as a physical phenomenon, requires a medium through which it can travel. On Earth, that medium is usually air. In water, it is the liquid itself. In solids, it is the material structure that carries vibrations. In the vacuum of space, there is no such medium. Without particles to transmit vibrations, sound waves cannot propagate. This means that even if something were to produce a vibration, there would be nothing to carry it across the vast distances. Within a supervoid, this absence becomes even more pronounced. Not only is there no atmosphere, but there is also very little matter of any kind. The sparse gas that exists is far too thin to carry sound in any meaningful way. The distances between particles are so large that vibrations dissipate almost immediately. The result is a silence that is not just quiet, but fundamentally different from anything we experience in everyday life. Imagining this kind of silence can be challenging. Our perception of sound is deeply tied to our sense of presence and awareness. Sound provides information about our surroundings, helping us detect movement, distance, and activity. It contributes to our sense of space, giving us cues about the environment we're in. Without it, the world feels different, less defined. In a supervoid, that absence of sound would be accompanied by a similar absence of visual complexity. The few distant galaxies would offer points of light, but they would be scattered and faint. There would be no nearby stars, no glowing clouds of gas, no clusters of activity. The combination of visual sparsity and absolute silence creates an environment that is both calm and difficult to fully comprehend. From a physical standpoint, this silence is entirely expected. Space is a vacuum, and supervoids are regions where that vacuum is even more pronounced. But from a human perspective, it can feel unusual because it removes one of the primary ways we interact with our surroundings. Without sound, there is no immediate feedback from the environment, no indication of movement or change. This raises an interesting question about perception. If you were in such a place, how would you experience it? Your senses would rely primarily on sight, but even that would be limited by the lack of nearby objects. Over time, the absence of sensory input might become more noticeable, not as discomfort, but as a kind of neutrality. The environment would not demand attention. It would simply exist, unchanged and unchanging on human timescales. There is also a deeper layer to this idea, one that connects to how we interpret silence in general. On Earth, silence can be associated with calm, rest, and stillness. It can also be associated with isolation or emptiness, depending on the context. In a supervoid, these associations merge. The silence is calm because there is nothing to disturb it, but it is also a reflection of the immense isolation of the region. At the same time, it is important to recognize that the universe itself is not entirely silent in an abstract sense. There are phenomena that can be described in terms of vibrations or waves, such as gravitational waves, which ripple through space-time itself. These waves are not sound in the traditional sense because they do not travel through a medium like air, but they represent a kind of cosmic signal, carrying information about events like the merging of black holes or neutron stars. In a supervoid, these signals would still pass through, undisturbed by dense matter. The region's emptiness allows such waves to travel freely without interference. While they would not be heard, they could be detected with the right instruments, providing a different kind of awareness of the universe's activity. There is also the cosmic microwave background, the faint radiation that fills all of space. While it does not produce sound, it represents a constant presence, a background signal that exists everywhere, including within supervoids. It is a reminder that even in the quietest regions, the universe is not entirely inactive. There are still subtle forms of energy and information moving through space. Considering this, the sound of silence in a supervoid is not a complete absence of activity, but rather the absence of the kinds of activity we are used to perceiving. It is a silence that exists because there is no medium for sound, no nearby objects to create it, and no frequent interactions to generate noise. It is a silence defined by the structure of the universe itself. From a reflective standpoint, this kind of silence can be seen as a different kind of environment, one that emphasizes stillness and continuity. Without sound to mark the passage of time or the presence of events, the experience becomes more about observation and less about interaction. The environment does not change quickly, and there are few signals to interpret. There is also a certain clarity in this. On Earth, sound can sometimes obscure or complicate our perception. It adds layers of information that require interpretation. In a supervoid, the absence of sound removes that layer, leaving a more direct relationship with the visual and spatial aspects of the environment. It simplifies the experience, even as it makes it more unfamiliar. At the same time, this simplicity highlights the scale of the universe. The silence is not just a lack of noise, but a reflection of the immense distances between objects. It is a consequence of the universe's structure, where matter is not evenly distributed, and where vast regions exist with very little to interact or communicate. The silence of a supervoid begins to feel less like an absence and more like a feature. It is part of what defines these regions, just as much as their size and their lack of galaxies. It is a natural outcome of the physical conditions that exist there, a reminder of how different the universe can be from our everyday experience. It's tempting to think of extremes in the universe as similar simply because they are unusual. A place with almost no matter and a place with far too much might seem, at a glance, like opposite sides of the same idea. And in a way, that instinct is not entirely wrong. Supervoids and black holes do represent two extremes, but they do so in very different ways. One stretches space into vast quiet openness, while the other compresses it into something intensely concentrated. Placing them side by side reveals not just contrast, but a deeper understanding of how the universe handles both absence and abundance. Let's begin with what defines each one. A supervoid is a region where matter is spread incredibly thin. Galaxies are few, distances are immense, and gravity is weak compared to other regions. There is no center pulling everything inward, no single defining object. Instead, the void is shaped by what has been drawn away from it, by the movement of matter toward denser areas elsewhere. A black hole, on the other hand, is defined by concentration. It forms when a large amount of matter collapses into a very small region, creating a gravitational field so strong that nothing can escape once it crosses a certain boundary. That boundary, known as the event horizon, marks a clear transition. Outside it, escape is possible. Inside it, it is not. This difference in structure is one of the most striking contrasts. Supervoids have no sharp edges. Their boundaries are gradual, blending into the surrounding cosmic web over vast distances. A black hole has a precise boundary, a surface of no return that can be calculated and defined. One fades into its surroundings. The other imposes a limit that cannot be crossed. Gravity behaves very differently in these two environments. In a supervoid, gravity is present but subtle. It gently guides galaxies outward, toward the filaments and clusters that surround the void. The overall effect is one of slow expansion and redistribution. In a black hole, gravity dominates completely. It pulls matter inward with increasing strength, distorting space-time and affecting everything nearby in dramatic ways. Light responds accordingly. In the presence of a black hole, light bends sharply, curving around the object and, if it comes too close, disappearing beyond the event horizon. This creates some of the most striking visual phenomena in the universe, including gravitational lensing and the bright rings of light sometimes observed around black holes. In a supervoid, light travels more freely. With less matter to influence it, its path is straighter, its journey less disturbed. Instead of being drawn inward, it simply passes through, subtly affected by the expansion of space. Time, too, reveals the contrast. Near a black hole, time slows down relative to distant observers. This effect becomes extreme near the event horizon, where the flow of time differs significantly depending on perspective. In a supervoid, the opposite trend exists, though far more gently. With less gravitational influence, time runs slightly faster compared to denser regions. The difference is small, but it reflects the same underlying principle. Gravity influences the passage of time. There is also a difference in how these environments evolve. Black holes can grow by accumulating matter. They can merge with other black holes, increasing in size and mass. Their influence extends outward, affecting nearby stars, gas, and even entire galaxies. Supervoids grow in a different way. They expand not by gathering matter, but by losing it. Matter flows outward toward denser regions, leaving the void increasingly empty. The growth is not about accumulation, but about separation. From a human perspective, the sense of danger is reversed. Black holes are immediately recognizable as hazardous. Their intense gravity poses a clear threat, and their behavior is dramatic and energetic. Supervoids, despite being described as unsettling, are not dangerous in a physical sense. They do not pull you in or trap you. If anything, they are among the safest regions in the universe in terms of immediate physical conditions. And yet, when people describe supervoids as scary, they're often referring to something different. It is not the threat of destruction, but the experience of emptiness. A black hole is frightening because of what it does. A supervoid can feel unsettling because of what it lacks. The absence of structure, the immense distances, and the lack of familiar reference points create a different kind of response, one that is more about perception than physical risk. Another interesting comparison lies in visibility. Black holes, despite their name, can often be detected through their effects on surrounding matter. Accretion disks glow brightly. Jets of energy extend across space, and nearby stars move in distinctive ways. Supervoids are harder to see because they do not produce such effects. They must be inferred from the distribution of galaxies and the behavior of light passing through them. In this sense, both are invisible in their own way, but one reveals itself through activity, while the other reveals itself through absence. Considering the larger cosmic structure, both play important roles. Black holes influence the evolution of galaxies, regulating star formation and shaping their surroundings. Supervoids influence the distribution of galaxies on the larger scales, helping define the cosmic web. They are part of the same universe, governed by the same physical laws, yet they represent very different outcomes of those laws. There is also a symmetry in how they challenge our intuition. Black holes push our understanding of gravity, density, and space-time to their limits. Supervoids challenge our understanding of emptiness, scale, and structure. One compresses matter to extremes, the other stretches it thin. Together they illustrate the range of possibilities that the universe can produce. Imagining a journey that passes near both environments highlights this contrast. Approaching a black hole, you would see increasing distortion, light bending, and time behaving differently. The environment would become more dynamic, more intense. Entering a supervoid, the opposite would occur. The environment would become simpler, quieter, less structured. The changes would be gradual, but the overall effect would be a reduction in complexity rather than an increase. There is also a difference in how these regions are studied. Black holes can be observed through relatively localized measurements, focusing on specific objects and their immediate surroundings. Supervoids require a broader perspective. They are understood through large-scale surveys and statistical analysis, requiring observations across vast regions of space. This difference reflects their nature, one concentrated and localized, the other extended and diffuse. From a conceptual standpoint, the comparison between voids and black holes offers a way to think about balance in the universe. Matter is not distributed evenly, and the extremes help define the structure as a whole. Dense regions pull matter together, while underdense regions allow it to spread out. The interplay between these extremes creates the patterns we observe from the smallest scales to the largest. Allowing this contrast to settle, it becomes clear that neither environment is more important than the other. They are complementary, each revealing different aspects of the same underlying reality. Black holes show us what happens when gravity dominates completely. Supervoids show us what happens when it becomes subtle and indirect. There is a quiet trick the universe plays, one that does not rely on illusions in the usual sense, but on the way light travels across unimaginable distances. Nothing is hidden, nothing is deliberately disguised, and yet what we see is not always a perfectly faithful picture of what is there. Between distant galaxies and our telescopes lies a vast landscape of matter and emptiness, and supervoids are part of that landscape. In their own subtle way, they shape the journey of light, creating what could be described as a kind of cosmic mirage. When we look out into space, we are never seeing objects as they are now. Light takes time to travel, and the farther away something is, the longer its light has been on the move. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. This alone already makes observation a kind of time travel. But there is another layer to this, something that happens during the journey itself. Light does not move through space as though it were an empty, unchanging stage. Instead, space is dynamic. It stretches, curves, and responds to the presence, or absence, of matter. Dense regions bend light inward, focusing it, sometimes magnifying distant galaxies in a phenomenon known as gravitational lensing. Supervoids, by contrast, do something more understated. They allow light to pass through with less interference, but in doing so, they introduce their own kind of distortion. The effect is not dramatic. You would not see a galaxy suddenly stretched into a ring or split into multiple images, as can happen near massive clusters. Instead, the influence of a supervoid is more like a gentle shift, a slight dimming, a subtle change in the energy of the light itself. As photons cross these vast underdense regions, they interact with the expanding fabric of space in a way that leaves a faint imprint. One of the key aspects of this process involves the way space expands over time. As light travels through a supervoid, the region itself is stretching, often slightly faster than denser areas, because there is less gravitational resistance. This means that the light's wavelength can be stretched a bit more than expected, reducing its energy. By the time it reaches us, it carries this subtle signature, a quiet indication that it has passed through an unusually empty region. From our perspective, this can alter how we interpret distant objects. A galaxy seen through a supervoid might appear slightly dimmer or cooler than it otherwise would. The effect is extremely small, and detecting it requires careful statistical analysis across many observations. Still, it is measurable, and it provides another way to map the structure of the universe. This is where the idea of a cosmic mirage begins to take shape. Not a mirage in the sense of seeing something that isn't there, but a gentle distortion that shifts our perception just enough to matter. The universe does not lie, but it does filter what we see through its structure. Supervoids, in their quiet way, are part of that filter. There is also a connection here to the cosmic microwave background, the ancient radiation we discussed earlier. As this background light travels through supervoids, it experiences the same subtle effects. The result is small variations in temperature, like the cold spot we explored before. These variations are not errors or noise, they are part of the signal, clues about the structure the light has passed through on its long journey to us. Another aspect to consider is how these effects accumulate. A single supervoid might only produce a tiny change in the light passing through it, but over billions of light years, light may cross multiple regions of varying density. Each one leaves its own faint imprint, and together they shape the final signal we observe. This makes the interpretation of cosmic data a complex task, requiring careful modelling of all the influences along the path. Astronomers account for this by combining observations with simulations. By recreating the large-scale structure of the universe in computational models, they can predict how light should behave as it travels through different environments. Comparing these predictions with actual observations helps identify where supervoids and other structures are influencing what we see. It is also worth noting that these effects are not limited to light alone. Other signals, such as gravitational waves, would also pass through supervoids with minimal interference. In some ways, these regions act as clear corridors through the universe, allowing certain forms of information to travel long distances without being significantly altered. At the same time, the expansion within these voids still leaves its mark, subtly modifying the signals in ways that can be detected with precise instruments. From a broader perspective, the idea of a cosmic mirage highlights the interconnected nature of the universe. What we observe is not just determined by the source of the light, but by everything it encounters along the way. Supervoids, despite their emptiness, are part of that journey. They influence how we perceive distant galaxies, how we measure cosmic expansion, and how we interpret the history of the universe. There is something quietly fascinating about this. The largest empty regions in the universe, places defined by what they lack, still have the power to shape what we see. They do not block light or distort it dramatically, but they leave a gentle signature, a trace that can be detected with enough care and precision. This also adds another layer to the challenge of understanding the universe. Observations must be interpreted in context, taking into account not just the objects themselves, but the paths their light has travelled. It is a reminder that seeing is not always straightforward, even when dealing with something as fundamental as light. At the same time, this complexity is part of what makes cosmology so rich. Each observation carries multiple layers of information, from the properties of the source to the structure of the space it has crossed. Supervoids contribute to this richness, offering both challenges and opportunities for discovery. The universe begins to feel less like a simple collection of objects and more like a layered system, where perception is shaped by both presence and absence. The cosmic mirage is not an illusion in the traditional sense, but a reflection of this layered reality, where even emptiness plays a role in what we observe. There comes a point in exploring the universe where observation begins to blur into speculation, not because the science becomes unreliable, but because the scale and nature of what we're studying push us right up against the edge of what we can currently test. Supervoids sit very close to that edge. They're real, measurable, and mapped with increasing precision, and yet, because they represent such extreme conditions of emptiness, they naturally invite questions that reach a little further, into ideas that are not yet fully settled. One of those ideas begins with a simple thought. If these regions are so vast, so underdense, so minimally interactive compared to the rest of the cosmic web, could they behave differently in ways we don't yet fully understand? Not in an obvious or dramatic sense, but in subtle ways that only become noticeable when we examine the universe on the largest possible scales. Within the standard model of cosmology, supervoids are explained quite well. They emerge from early density fluctuations, grow through gravitational dynamics, and continue expanding as matter flows toward denser regions. Their properties match simulations, and their effects, such as the slight cooling of background radiation, are consistent with known physics. In that framework, there is no need to invoke anything unusual. Emptiness is simply a natural outcome of the universe's evolution. Still, the human tendency to ask "what if" doesn't entirely fade away, especially in places where the usual rules feel stretched thin. Because supervoids contain so little matter, they are sometimes considered environments where certain effects might be easier to isolate. In dense regions, many forces and interactions overlap, making it harder to disentangle one influence from another. In a supervoid, the lack of interference creates a kind of simplicity. This simplicity allows scientists to test whether the laws we observe locally hold true across vast, nearly empty regions of space. One area where this becomes particularly interesting is in the study of dark energy. This mysterious component of the universe is responsible for its accelerated expansion, yet its nature remains unknown. In dense regions, gravity partially counteracts this expansion. In supervoids, with much less matter present, dark energy's influence becomes relatively stronger. This has led to careful studies of how galaxies move within and around voids, searching for subtle deviations from expected behaviour. So far, the results largely support existing models. The universe behaves consistently, even in its emptiest regions, but the precision of these measurements continues to improve, and supervoids remain one of the best environments for testing whether something unexpected might be hiding within the data. Another line of thought considers the possibility that our understanding of gravity itself might not be complete. Some alternative theories propose that gravity behaves differently on very large scales or in low-density environments. If that were the case, supervoids could serve as natural testing grounds. Their sparse matter and immense size make them ideal for detecting even small deviations from the predictions of general relativity. Again, no clear evidence has yet confirmed such deviations, but the question remains open. The universe has a history of surprising us, and places that seem simple often turn out to hold deeper complexity when examined closely enough. Moving a little further into speculative territory, some theorists have considered whether supervoids could be connected to larger structures or phenomena beyond our observable universe. This idea doesn't suggest that voids are portals or boundaries in a literal sense, but rather that they might reflect variations in the universe's structure on scales even larger than what we can currently observe. In certain models, the universe could be part of a larger multiverse, where different regions have slightly different properties. If such a scenario were true, it's possible that large-scale features like supervoids could be influenced by conditions beyond our observable horizon. This remains highly theoretical, with no direct evidence, but it illustrates how studying extreme environments can lead to broader questions about the nature of reality. The phrase "parallel nothingness" captures this idea in a more poetic way, though we can keep it grounded. It refers not to literal parallel worlds hiding inside voids, but to the notion that emptiness itself might have layers of meaning we haven't fully explored. A supervoid is already an extreme case of low density, but when you consider how little we know about dark matter, dark energy, and the large-scale geometry of the universe, it becomes clear that even nothing can still contain unanswered questions. There is also an interesting conceptual parallel with quantum physics. At very small scales, what we think of as empty space is not truly empty. It is filled with fluctuations, temporary particles appearing and disappearing, a kind of restless background activity. On the larger scales, supervoids represent the opposite extreme, where space appears as close to empty as possible in a cosmological sense. Yet even here, there is still dark matter, diffuse gas, and the ever-present expansion of space. This contrast between small-scale, full emptiness and large-scale, quiet emptiness highlights how the idea of nothingness changes depending on context. In quantum terms, nothing is active and fluctuating. In cosmological terms, nothing is vast and still. Supervoids sit firmly in the latter category, but they remind us that emptiness is never absolute. Another angle to consider is how observers within different regions of the universe might perceive it. If you were located deep inside a supervoid, your view of the cosmos would be different from ours. The distribution of galaxies would appear more sparse, the cosmic web less obvious. Over time, as the universe continues to expand, distant structures would move further away, eventually becoming undetectable. In such a scenario, an observer might conclude that the universe is far more empty and uniform than it actually is. Their cosmological models could differ significantly from ours, simply because their vantage point provides less information. This idea has been explored in theoretical studies, showing that location within the cosmic web can influence how the universe is perceived and understood. This doesn't imply multiple realities, but it does suggest multiple perspectives within the same reality. In that sense, parallel nothingness can also be understood as different experiences of emptiness depending on where you are in the universe. Reflecting on all of this, it becomes clear that supervoids are not just empty spaces to be mapped and measured. They are environments that invite deeper questions, not because they behave in obviously strange ways, but because their simplicity allows us to test the boundaries of our understanding. At the same time, it's important to stay grounded in what we know. The current evidence supports a consistent picture of the universe, where supervoids are natural outcomes of cosmic evolution. They do not appear to hide exotic phenomena or alternate realities. Their behavior aligns with established physics, and their properties can be explained within existing models. And yet, the fact that we can even ask these questions, that we can consider the possibility of deeper layers within emptiness, is part of what makes studying the universe so compelling. Supervoids, by stripping away complexity, leave us with a clearer view of the underlying structure, and in doing so, they highlight both what we understand and what remains uncertain. The idea of parallel nothingness becomes less about hidden worlds and more about the richness of inquiry itself. Even in the emptiest regions, there is room for curiosity, for careful testing, and for the gradual expansion of knowledge. Long after the discovery that the universe is expanding, a second, more surprising realization began to take shape. Not only is space stretching, but that stretching is speeding up. Galaxies are not just drifting apart, they're accelerating away from one another over time. This discovery introduced one of the most puzzling components in modern cosmology, something we now call dark energy. It is not something we can see or touch, and yet it appears to make up the majority of the universe, quietly driving its expansion on the larger scales. Within this picture, supervoids take on a particularly interesting role. These vast regions of low density, already defined by their emptiness, are places where the influence of dark energy becomes more noticeable. Not because dark energy is stronger there in an absolute sense, but because there is less matter to counteract it. In denser regions, gravity pulls inward, partially resisting the expansion of space. In supervoids, that resistance is weaker, allowing the effects of expansion to show themselves more clearly. To understand this, it helps to think about the balance between two influences. On one side, gravity works to pull matter together, slowing down expansion locally and creating structures like galaxies and clusters. On the other side, dark energy acts in the opposite direction, pushing space apart and accelerating the overall expansion of the universe. The interplay between these two determines how different regions evolve over time. Inside a supervoid, gravity has less to work with, there are fewer galaxies, less dark matter, and less overall mass to generate a strong inward pull. As a result, dark energy's effect is relatively more prominent. The space within and around the void can expand more freely, contributing to the gradual growth of the void itself. Over billions of years, this leads to an increasing separation between galaxies, making these regions even emptier. This process is subtle. There are no sudden jumps or dramatic changes that would be noticeable on short timescales. Instead, it unfolds slowly, with galaxies drifting farther apart, distances increasing almost imperceptibly. But when considered over the age of the universe, the cumulative effect is significant. Supervoids become larger, their interiors more sparse, and their influence on the surrounding structure more pronounced. One way scientists study this relationship is by observing how galaxies move in and around voids. As we've discussed, galaxies tend to drift outward from the centres of voids, drawn toward denser filaments. This motion is influenced both by gravity and by the expansion of space. By measuring these movements, astronomers can test whether they match the predictions of models that include dark energy. So far, observations have been consistent with the idea that dark energy behaves uniformly across the universe. Supervoids do not appear to contain a different kind of dark energy, nor do they amplify it beyond what is expected. Instead, they act as environments where its effects are easier to observe, simply because there is less competing influence from gravity. There is also a connection between supervoids and how we measure the expansion of the universe itself. Many of the methods used to determine the rate of expansion rely on observing distant objects, such as supernovae or galaxies, and analysing how their light has been stretched over time. As this light travels across the universe, it passes through regions of varying density, including supervoids. The presence of these voids can introduce small effects in the measurements. For example, light passing through a supervoid may experience slightly more redshift due to the expansion of space within that region. While these effects are typically very small, they must be accounted for when making precise cosmological measurements. In this way, supervoids become part of the process of understanding dark energy, influencing the data that scientists use to study it. Another area of interest is how supervoids contribute to large-scale patterns in the universe. Because they expand and grow over time, they help shape the overall distribution of matter. This, in turn, affects how galaxies cluster and how the cosmic web evolves. Dark energy plays a role in this evolution, influencing the rate at which structures form and the way voids expand. Computer simulations are particularly useful in exploring these relationships. By modelling the universe with different assumptions about dark energy, scientists can see how the size and distribution of voids would change. Comparing these simulations with actual observations helps refine our understanding of both voids and dark energy, providing constraints on how this mysterious component behaves. There's also a broader implication to consider. If dark energy continues to drive accelerated expansion, the future of the universe may become increasingly dominated by emptiness. Over extremely long timescales, galaxies outside our local group will move farther and farther away, eventually becoming undetectable. The cosmic web will stretch, filaments will thin, and supervoids will grow even larger. In such a future, the universe would appear far more empty than it does today. Observers in that distant era might see only a handful of nearby galaxies, with the rest of the universe receding beyond the observable horizon. Supervoids, already vast, would become even more dominant, shaping the large-scale structure in a way that emphasizes emptiness over density. This perspective highlights how supervoids are not just features of the present universe, but also indicators of its long-term evolution. They show us what happens when expansion continues over billions or trillions of years, when the balance between gravity and dark energy shifts further toward expansion. At the same time, it is important to remember that dark energy remains one of the least understood aspects of cosmology. We know how it behaves on large scales, but we do not yet know what it is. It could be a property of space itself, a kind of energy inherent to the vacuum. It could be something more complex, involving fields or phenomena that we have yet to fully describe. Supervoids, with their low density and large scale, provide one of the best environments for testing these ideas. By studying how they grow, how galaxies move within them, and how they influence light and radiation, scientists can gather clues about the nature of dark energy. Each observation adds a piece to the puzzle, helping to narrow down the possibilities. Reflecting on this, there is a certain elegance in how emptiness becomes a tool for understanding one of the universe's greatest mysteries. Supervoids, defined by what they lack, become places where the effects of dark energy can be observed more clearly. They are not just passive gaps, but active participants in the unfolding story of cosmic expansion. Allowing this understanding to settle, the relationship between supervoids and dark energy begins to feel less abstract and more intuitive. In regions where there is less matter, the influence of expansion becomes more visible. In regions where there is more matter, gravity competes more strongly. The universe, in this sense, is a balance of forces, with supervoids representing one side of that balance. Imagine trying to point to the nearest neighbour, not across a street, not across a city, but across tens of millions of light years. Not a faint glow just beyond the horizon, but something so distant that even light, moving as fast as anything can, would take longer than human history has existed just to arrive. In a supervoid, this is not an exaggeration. It is the baseline. This is what proximity looks like there. And within that reality, the idea of loneliness takes on a scale that feels almost impossible to translate into everyday terms. On Earth, loneliness is something we understand through experience. It might mean being physically alone, or feeling disconnected from others even in a crowd. It is shaped by communication, by presence, by the ability to interact and respond. Even at its most intense, it exists within a world that is still full of life, sound, and movement. There is always the possibility of connection, even if it feels distant. In a supervoid, the concept shifts from emotional to physical, from feeling to structure. It is not about awareness or perception, but about actual separation. Galaxies, entire collections of billions of stars, exist in isolation so complete that interaction becomes extraordinarily rare. The distances are so vast that even gravitational influence, which extends across space, becomes faint and indirect. If you were to place a galaxy deep within a supervoid and ask how often it might meaningfully interact with another, the answer would be measured not in years or centuries, but in billions of years, if at all. Collisions, which are relatively common in dense clusters, become almost non-existent. The exchange of gas, the merging of structures, the dynamic reshaping that defines galaxy evolution elsewhere, slows to a near standstill. This kind of isolation affects how galaxies live their lives. Without frequent interactions, their evolution becomes quieter, more self-contained. Star formation proceeds at a slower pace, often limited by the available gas within the galaxy itself. There are fewer external triggers to spark bursts of activity, fewer opportunities for dramatic change. Over time, these galaxies can become more stable, but also more subdued, their brightness and structure reflecting a long history of minimal disturbance. There is also the matter of communication, if we imagine it in a purely physical sense. Signals, whether in the form of light or any other electromagnetic radiation, travel at a finite speed. In a supervoid, the distances involved mean that any signal sent from one galaxy to another would take millions or even hundreds of millions of years to arrive. By the time it reached its destination, the sending galaxy might have changed significantly, or the receiving galaxy might have evolved in ways that make the original message almost irrelevant. This creates a kind of temporal isolation layered on top of the spatial one. Not only are galaxies far apart, but their ability to share information is delayed to such an extent that real-time interaction is effectively impossible. Each galaxy becomes, in a sense, its own self-contained system, evolving according to its internal conditions and the slow influence of the broader cosmic environment. From a human perspective, it is natural to try to project feelings onto this scenario, to imagine what it would be like to exist in such isolation. But it is important to remember that galaxies do not experience loneliness in the way we do. They do not have awareness or emotion. Their loneliness is purely a matter of distance and interaction, not feeling. And yet the concept still resonates, because it reflects something fundamental about connection and separation on a universal scale. There is also an interesting contrast between this kind of isolation and the interconnected nature of the cosmic web. While supervoids represent regions of extreme separation, they are still part of the larger structure. The galaxies within them are not entirely disconnected from the rest of the universe. They are influenced by the gravitational pull of distant filaments and clusters, even if that influence is weak. They are part of the same expanding space, the same overall system. This means that the loneliness of a supervoid is not absolute in a structural sense. It is relative, defined by the scale of separation rather than complete disconnection. The galaxies within a void are still linked, however faintly, to the rest of the cosmos. Their isolation is immense, but not total. Another layer to consider is how this isolation changes over time. As the universe continues to expand, driven by dark energy, the distances between galaxies increase. In supervoids, where expansion is less constrained by gravity, this effect can be even more pronounced. Galaxies that are already far apart drift even farther, deepening the separation. Looking far into the future, this process leads to a scenario where the universe becomes increasingly isolated. Distant galaxies move beyond the observable horizon, their light no longer able to reach us. From the perspective of any given galaxy, the universe appears to shrink, not in physical size, but in observable content. What was once a richly connected cosmic web becomes a much sparser view, with only nearby structures remaining visible. In such a future, the kind of isolation we see in supervoids today could become more common, extending across larger regions of space. The universe, in a sense, would become more lonely, not because anything is being lost locally, but because the connections between distant regions are stretched beyond the limits of observation. Reflecting on this, there is a subtle shift in how we think about our own place in the universe. We exist in a relatively dense region, with nearby galaxies, stars and planets, providing a sense of connection and structure. The night sky is filled with points of light, giving us a visual reminder of the universe's richness. But this is not the universal experience. There are places where the sky would look very different, where the sense of connection is far less immediate. This perspective can be both humbling and calming. It highlights the diversity of environments within the universe, showing that what we experience locally is just one part of a much larger picture. It also emphasizes the idea that connection, whether physical or conceptual, depends on scale and context. At the same time, the concept of loneliness on a galactic scale does not have to carry a negative meaning. In the absence of frequent interaction, there is also stability. There is space for slow, steady evolution, for processes that unfold without interruption. The quiet of a supervoid is not just emptiness, but a different kind of environment, one where change happens gently and over long periods. The vast separation between galaxies begins to feel less like a void in the emotional sense and more like a feature of the universe's structure. It is part of how the cosmos organizes itself, balancing regions of density with regions of openness. At some point in any exploration of the universe, there comes a quiet realization that what we know, even when it feels vast, is still only a small portion of what there is to understand. Not because the knowledge is incomplete in a careless way, but because the universe itself is so large, so subtle, and so patient that it always extends beyond the limits of our current reach. Supervoids bring us very close to that boundary, not because they are chaotic or unpredictable, but because they are so simple, so empty. that they strip away complexity and leave us facing the fundamentals. In regions filled with galaxies, clusters, and interactions, there are many signals to study. Light is abundant, motion is easier to detect, and events provide clear markers for observation. In a supervoid, much of that is absent. There are fewer galaxies to measure, fewer interactions to observe, and fewer immediate clues to guide interpretation. This does not make these regions unimportant. In fact, it makes them particularly valuable because they offer a clearer view of the underlying structure of the universe, with less interference from local complexity. Still, that clarity comes with limits. Detecting something that is defined by absence requires careful inference. Mapping supervoids depends on large datasets, statistical analysis, and indirect measurements. We are not observing a solid object or a bright source of radiation. We are observing patterns, differences, and subtle effects. This means that our understanding is always tied to the precision of our instruments and the depth of our data. As our tools improve, so does our ability to explore these regions. Larger surveys map more galaxies, extending our view deeper into space. More sensitive instruments detect smaller variations in background radiation, revealing finer details in the cosmic microwave background. Simulations become more detailed, allowing us to compare theoretical models with observations more accurately. Each of these advances pushes the boundary of what we can know a little further outward, and yet, even with these advances, there are limits that are not easily overcome. One of the most fundamental is the observable universe itself. We can only see as far as light has had time to travel since the Big Bang. Beyond that horizon, there may be more structure, more voids, more patterns, but they remain inaccessible to direct observation. Supervoids that lie near the edge of what we can observe are particularly interesting, because they hint at structures that may extend beyond our visible reach. There is also the limitation imposed by time. The light we observe from distant regions shows us the past, not the present. When we map a supervoid billions of light years away, we are seeing it as it was billions of years ago. Its current state, if it has changed, remains unknown to us. This means that our understanding of the universe is always a combination of different moments in time, stitched together into a coherent picture. Another layer of uncertainty comes from the components of the universe that we do not fully understand. Dark matter and dark energy make up most of the universe's content, yet their nature remains largely unknown. Supervoids, being regions where these components play a significant role, are directly connected to these mysteries. While we can measure their effects, we do not yet have a complete explanation for what they are or how they behave at the most fundamental level. This is where supervoids become particularly intriguing. Their simplicity makes them ideal testing grounds for theories about dark matter and dark energy. With fewer competing influences, it becomes easier to isolate the effects of these components and compare observations with predictions. Any deviation from expected behavior could point to new physics, offering clues about the nature of the universe that go beyond our current models. At the same time, the absence of clear anomalies is also informative. The fact that supervoids behave largely as predicted reinforces the validity of our current understanding. It shows that the same physical laws apply across a wide range of environments, from dense clusters to vast empty regions. This consistency is one of the strengths of modern cosmology, providing a unified framework that describes the universe on many different scales. Still, the boundary remains. There are questions we cannot yet answer. How exactly did the initial fluctuations in the early universe arise? What is the true nature of dark energy? Does the universe extend infinitely beyond what we can observe? Or does it have a larger structure that we have not yet detected? Supervoids do not answer these questions directly, but they are part of the path toward understanding them. There is also a philosophical aspect to this boundary. Exploring the edge of knowledge is not just about gathering more data or refining models. It is also about recognizing the limits of what can be known at a given time. In the context of supervoids, this means accepting that some aspects of these regions, especially those related to the broader structure of the universe, may remain uncertain until new methods or technologies are developed. This recognition does not diminish the value of what we have learned. Instead, it adds depth to it. Knowing where the limits are helps define the scope of our understanding and highlights the areas where further exploration is needed. It turns uncertainty into a guide rather than a barrier. From a more reflective perspective, there is something fitting about encountering the edge of knowledge in the study of emptiness. Supervoids, defined by their lack of matter, lead us to questions defined by our lack of complete understanding. The parallel is subtle, but it reinforces the idea that absence, whether physical or conceptual, can be just as informative as presence. At the same time, the process of pushing this boundary forward is ongoing. Each new observation, each improved measurement, each refined simulation contributes to a more detailed picture of the universe. The edge of knowledge is not fixed. It moves outward as we learn more, revealing new questions even as it answers old ones. Considering this, the study of supervoids becomes part of a larger journey, one that extends beyond any single discovery or theory. It is about gradually expanding our view, piece by piece, across scales that are almost beyond comprehension. It is about learning to interpret patterns in both presence and absence, to read the structure of the universe in its densest regions and its emptiest ones alike. The edge of knowledge feels less like a boundary to be reached and more like a horizon to be approached. Always just a little further away, supervoids guide us toward that horizon, offering a clearer view of the universe's simplest structures and, in doing so, pointing us toward the deeper questions that remain. If you were to step back far enough to take in the entire universe at once, not as a collection of individual galaxies, but as a single evolving structure, something unexpected would begin to stand out. It would not be the brightest clusters or the most massive galaxies that define the overall shape. Instead, it would be the contrast, the pattern formed by what is there and what is not. The filaments would trace long, delicate lines, the clusters would mark intersections, and between them, the vast open regions of supervoids would quietly define the boundaries of everything else. In that sense, supervoids act like architects, not because they actively build structures, but because they shape the space in which those structures form. They determine where matter is not, and by doing so, they influence where matter gathers. Without these immense regions of low density, the cosmic web would not have the same clarity or form. The filaments would not stand out as they do, and the large-scale structure of the universe would appear far more uniform and less organized. This idea can feel counterintuitive at first. We tend to associate creation with presence, with the accumulation of material, with the building of something tangible. But in the universe, absence plays an equally important role. The distribution of matter is not just about where it exists, but also about where it has been drawn away from. Supervoids are the result of that redistribution, and in turn they reinforce it, guiding the flow of matter over billions of years. Gravity, as we've explored, is central to this process. It pulls matter toward denser regions, strengthening filaments and clusters. As matter moves outward from voids, it leaves behind increasingly empty spaces, which then expand further as the universe itself grows. This creates a feedback loop. The emptier the void becomes, the more it contributes to the contrast between dense and sparse regions, sharpening the overall structure of the cosmic web. From this perspective, supervoids are not passive gaps, but active participants in shaping the universe. They influence the movement of galaxies, the distribution of dark matter, and the pathways along which gas flows. They help define the routes that matter takes as it travels through the cosmic web, guiding it toward the dense nodes where galaxies cluster and evolve. There is also a geometric aspect to this role. The universe on large scales can be thought of as a kind of three-dimensional network, where the arrangement of voids and filaments creates a pattern that repeats across vast distances. Supervoids act as the spaces within this pattern, giving it structure and coherence. Without them, the network would collapse into a more uniform distribution, lacking the intricate detail that we observe. Observations and simulations both support this view. When scientists model the evolution of the universe, they see voids forming naturally as matter flows toward denser regions. These voids grow and merge, creating larger structures that define the layout of the cosmic web. The resulting pattern closely matches what we observe in galaxy surveys, reinforcing the idea that supervoids are fundamental to the universe's architecture. Another important aspect of their role involves scale. Supervoids operate on the largest scales we can observe, spanning hundreds of millions of light years. Their influence is not local or immediate, but broad and gradual. They shape the universe over billions of years, guiding the overall distribution of matter rather than affecting individual objects in dramatic ways. This slow, large-scale influence can be easy to overlook, especially when compared to more dynamic phenomena like supernovae or black holes. But it is precisely this steadiness that makes supervoids so important. They provide a kind of background framework, a structure that evolves quietly but consistently, shaping everything else that occurs within it. There is also a connection between supervoids and the expansion of the universe. As we discussed earlier, these regions tend to expand more freely due to their low density. This contributes to the overall growth of the cosmic web, stretching the distances between filaments and clusters. In this way, supervoids are linked to the broader dynamics of cosmic expansion, participating in the same processes that govern the universe as a whole. From a conceptual standpoint, thinking of supervoids as architects helps shift our perspective. It encourages us to see the universe not just as a collection of objects, but as a system defined by relationships and patterns. The presence of galaxies is important, but so is the absence between them. Together, they create a structure that is more than the sum of its parts. This perspective also highlights the interconnected nature of the cosmos. Supervoids may seem isolated, but they are deeply connected to the filaments and clusters that surround them. Their existence depends on the movement of matter toward those denser regions, and in turn they help shape how that movement occurs. The universe is not divided into separate components, but woven together into a continuous whole. Reflecting on this, there is something quietly elegant about the role of supervoids. They do not shine or emit energy in dramatic ways. They do not attract attention through brightness or activity. Instead, they contribute through absence, through the space they provide, through the structure they help define. It is a kind of influence that is easy to miss, but essential once understood. This idea can also be extended to how we think about complexity and simplicity. The universe, in its vastness, contains both intricate structures and simple patterns. Supervoids represent one of the simplest aspects, regions of low density and minimal interaction. Yet, from this simplicity, emerges a crucial contribution to the overall complexity of the cosmic web. Allowing this understanding to settle, the image of the universe becomes more balanced. It is not just a place of dense clusters and bright galaxies, but also of vast, quiet spaces that shape the whole. Supervoids, as the quiet architects, provide the framework within which everything else exists. Take a moment to let the scale settle in, not all at once, but gradually. There is no need to rush it. The universe we've been moving through, from galaxies to supervoids to the vast network that connects them, does not reveal itself quickly. It unfolds slowly, piece by piece, as the mind adjusts to distances and structures that are far beyond everyday experience. And somewhere within that process, something shifts, not in the universe itself, but in how we relate to it. Up to this point, we've been looking outward, examining structure, motion, gravity, and light. We've traced how supervoids form, how they grow, how they influence everything around them. But now, the perspective gently turns inward, not to leave the science behind, but to sit with what it implies. Because when you consider something as vast as a supervoid, something so large that entire galaxies are reduced to distant points within it, it naturally invites reflection. On a human scale, space often feels large enough already. The distance between cities, between continents, even between Earth and the Moon can feel significant. When we expand that perspective to include the solar system, the distances become harder to visualize. And yet, all of that still fits comfortably within a region that is tiny compared to a single galaxy. A galaxy, in turn, is only a small part of a cluster, and clusters are just nodes within the cosmic web. Supervoids stretch across all of this, encompassing distances so immense that the usual comparisons begin to lose their meaning. This is where contemplation begins to take a different form. It is no longer about calculating distances or understanding processes, but about allowing the scale itself to exist in your awareness, even if it cannot be fully grasped. There is no expectation that the mind will perfectly visualize 1 billion light years. It is enough to recognize that such distances exist, and that they are part of the same universe we inhabit. There is something quietly grounding about that realization. The universe does not separate itself into the familiar and the incomprehensible. It is one continuous structure, ranging from the smallest particles to the largest voids. The same physical laws apply across all scales, linking everything together in a way that is both simple and profound. At the same time, contemplating this vastness can shift how we think about importance and scale in our own lives. On one hand, it can feel humbling. The distances are so great, the structures so large, that individual experiences seem small in comparison. A single lifetime, even the entire span of human history, is brief when measured against billions of years. But there is another side to this perspective, one that is often overlooked. The fact that we can observe, measure, and think about these vast structures is itself remarkable. The same universe that contains supervoids also contains the conditions necessary for awareness, for curiosity, for the ability to ask questions about its own nature. In that sense, the smallness of our scale does not diminish our significance. It highlights the uniqueness of our perspective. Supervoids in particular offer a kind of clarity in this reflection. Their emptiness strips away much of the complexity that fills other regions of the universe. They present a simpler backdrop, a reminder that structure emerges from contrast, that presence is defined by absence, and that even the quietest regions play a role in shaping the whole. There is also a sense of continuity that comes with this contemplation. The light we see from distant galaxies has travelled for billions of years, crossing supervoids, passing through filaments, carrying with it information about the past. When we observe it, we're not just looking at distant objects, but participating in a chain of events that spans the history of the universe. The present moment becomes connected to the distant past in a very literal way. This connection can feel calming. The universe is not static, but it is also not chaotic in the sense of being random or disconnected. It evolves according to consistent principles, forming patterns that can be observed and understood. Supervoids, with their slow expansion and quiet presence, are part of that steady evolution. Allowing the mind to rest in this idea, the vastness begins to feel less overwhelming and more expansive in a different sense. It opens space for thought, for a perspective, for stepping outside the immediate concerns of daily life. The scale of the universe does not demand anything from us. It simply exists, offering a broader context within which everything else takes place. There is also a subtle shift in how we perceive emptiness itself. In everyday language, emptiness often carries a negative connotation, suggesting a lack or absence that needs to be filled. In the context of the universe, emptiness is not a deficiency. It is a fundamental part of structure, a necessary component of the cosmic web. Supervoids are not missing something they should have. They are exactly what the universe has formed them to be. This reframing can extend beyond cosmology. It suggests that absence, space, and stillness have value in their own right. Just as supervoids allow the cosmic web to take shape, Moments of quiet and openness can provide structure in other contexts. It is not a direct comparison, but it echoes the same idea, that balance between presence and absence is part of how systems, whether cosmic or personal, organize themselves. Returning to the universe itself, the image that emerges is one of balance and contrast. Dense clusters and vast voids, bright galaxies and dark spaces all connected within a single evolving system. Supervoids, despite their emptiness, are integral to that system, shaping its form and influencing its dynamics. The question of scale becomes less about trying to comprehend every detail, and more about recognizing the range that exists. From the smallest measurable units to the largest observable structures, the universe spans an extraordinary spectrum. Supervoids occupy one end of that spectrum, representing the extremes of emptiness and distance. Now, as everything we've explored begins to settle, there is no need to hold on to every detail. The names, the distances, the structures, they can gently drift into the background. What remains is the feeling of scale, the quiet understanding that the universe is vast beyond measure, and that within it exist these enormous regions where almost nothing happens, where time stretches, where light travels undisturbed, and where silence is complete. There is something naturally calming about that idea when you allow it to rest without resistance. Supervoids, despite their intimidating size, are not places of chaos or danger. They are steady, they're quiet. They change so slowly that even billions of years pass like a soft, unbroken moment. Nothing rushes there. Nothing demands attention. The universe in those regions is patient, and in a way, that patience can be shared. Imagine yourself drifting, not falling, not moving quickly, just gently existing within that immense space. There is no need to orient yourself, no need to find direction. The distances are too large for urgency to matter. The nearest galaxy is far away, its light faint but steady, a quiet reminder that structure still exists, even across such vast emptiness. There is no sound, not the kind we're used to, not footsteps, not wind, not distant noise, just a complete stillness where nothing vibrates through the space around you. And rather than feeling unsettling, it begins to feel neutral, almost comforting in its consistency. There are no interruptions, no sudden changes, only a continuous gentle quiet. Breathing slows naturally in that kind of stillness. There is nothing to react to, nothing to anticipate. The mind, which often looks for patterns, for movement, for something to focus on, gradually realizes that it does not need to search. The space itself is enough. The absence of distraction becomes a kind of presence, something steady to rest within. Far in the distance, light continues its journey. Photons that have travelled for millions or billions of years pass silently through the void, carrying with them the history of the universe. They do not hurry, they do not change course, they simply move, steady and consistent, crossing distances that are difficult to imagine, yet doing so without effort. Time continues as well, but here it feels different. Not because it has changed physically, but because there are no events to divide it. No ticking markers, no clear beginnings or endings, just a smooth, continuous flow. Moments are not counted. They are experienced as part of an unbroken whole, and within that there is space to rest. The vastness does not need to be understood all at once. It does not need to be measured or analysed. It can simply be acknowledged, allowed to exist as something larger than thought, something that does not require effort to hold in the mind. Supervoids, the quiet giants of the universe, become less about emptiness and more about stillness. They remind us that not everything needs to be filled, that not every space needs to contain activity. Some regions exist simply as they are, expansive and calm, shaping the universe without drawing attention to themselves. And as you remain here, just for a moment longer, there is no need to move on quickly. The galaxies will continue their slow drift. The cosmic web will stretch and evolve. The light will keep travelling unchanged in its quiet persistence. Everything continues whether observed or not. You can let your thoughts soften, just as the universe does in these vast regions. No sharp edges, no urgency, just a gradual easing into stillness. And as the idea of that immense silent space settles more deeply, it becomes something you can carry with you, not as a concept to analyse, but as a feeling of openness, of calm, of scale that gently places everything into perspective. The universe does not rush, and neither do you have to. So for now, you can simply rest here, in the quiet, in the distance, in the soft, endless silence of space, where even the larger structures fade into stillness, and where nothing is required except to drift, slowly and peacefully, into rest.